Okay, so take a deep breath and start. No one's saying anything. Everyone's like so quiet. Oh, look, it's all like coming in. Hi, good evening to everybody. Cool. Or good morning if you're somewhere else. China plus 16 hours. Okay, cool. Yeah, good evening. Good, Rimani. Hello, Akash. Good. Karishma, Rimani, Julian, Vaishnavi. Okay, Shobit. Hi, everyone. So I'm gonna start showing you what we have for today, which is let's get started. Go over here. Five and hey, cool. So our plan for today goes something like this. Okay, we want to finish up our BI discussion because now you understand. Curious to hear the description of your latest desktop. Oh, yeah, I know. Yeah, I'll just spend 1 minute on that. I'll come back to that. Well, I'll tell you now. Actually, yeah, it's more like an ice cream cone. Okay, a little ice cream cone, and here there's a little bit of Neapolitan, ice cream action going on. And then at the back over here might be called a mango sherbet. Exactly, it's an ice cream. And then way on the back, it's some kind of coffee caramel ice cream. A little bit of everything. And then they're all saying, "Eat me!" I'm like, okay. Except there's actually another character. Okay, so these two eyes belong to this character. There's a different eye that is being blocked by this eye. Yeah, exactly. I scream, you scream, we all scream for ice cream. That's exactly where that came from. Very good. I scream. You scream. Cool. Okay, so yeah, well, finish up BI. BI is a very interesting idea. Organizations do it all the time. And so I want to tell you about the whole cube roll up, all that extension. Also, just for the record, anything that we say today is not going to be on the midterm, which by the way is just 2 days away. Cool. And then I'm going to definitely talk about spatial data. So, for example, from Google Earth, you can see anybody's house in the world. And so if you're having your roof redone, yeah, definitely be sure to pay them well. Otherwise, this is the graffiti they're going to put on your roof. And the whole world can see it. Is it possible to fix the slides on the course site to be centered? I don't know what you mean. I'm just scrolling for now, okay? Are you talking about in general or are you talking about right now? Well, you can answer me, okay, in a little bit. But yeah, exactly. So definitely be nice to your roofers. Otherwise, it's forever. And then this is like home prices and so on in like Los Angeles. It's spatial data. So I want to tell you a lot about spatial data, and you will get a homework on spatial data. And then we'll only do a part of this. I want like rush like lots of different things today. We'll definitely get started on NoSQL. So NoSQL is the big revolution that came along with the internet, which is when slowly but surely relational databases, as great as they are slowly increasingly being used less and less. So what replaces them is the idea of a NoSQL database. And in a NoSQL database, the main thing that makes it NoSQL is there's no tables at all. Haha, there's a little joke there. Cool. As opposed to a bunch of SQL admins walk into a bar and say, mind if I join you? I get it, join. But here, they can't try anything. They just have to go. Um, Probably next week. Yeah, possibly over the weekend, but if not, for sure next week. Because I'm trying to modify like aspects of what I've said in the past. It's going to be like lots of very cool visualization. It might involve some Python, some R, and some JavaScript. Hey, why not? Just use up every single language that there is. Probably some Wolfram as well. It's a programming language called Wolfram. Yeah, there's a mild session. So we'll start that at about 8 o'clock, okay? So roughly 20 minutes, there's a pretty mini review session where you'll still do most of the talking. I'll ask you some questions. Hey, cool. So with all that out of the way, so we have to do some of this BI stuff. See, this is what it looks like, okay? So I'll do this, I'll definitely do this, and then we'll do some of this because we can always continue. That's one big, excuse me, oops, one big topic right there. So it'll all like work out nicely. Okay, so BI. Here's what I mean instead of looking at I see. Okay, this might be useful. I'm going to print that. Imager. Oh, I see. So you want it to be like centered here. Okay. example there. Yeah, I'll see what I can do. Okay, there's like a reason why I pretty much like line it all to the left, but maybe we can have it centered. It's actually an easy thing. I'll do it afterwards. Okay. We'll try it for a few more classes and see what happens. Like see like right there, all of that can easily be centered. So we can try it. Since you have a large monitor. Okay. All right. So, but for now we're gonna go with this. Okay. 100%. Yeah, I made it a little bit smaller because then if we want, we can make it bigger like that. Oops, it went the other way. Oh, never mind. Okay. If that's pretty odd. What if you go smaller? Then it's just the same. It actually, yeah. Okay, that's all like silly stuff. Okay, we can read this. The point about BI is the main idea. It's like right here. Got a little small. You take basically external data. In other words, these are and operational data. These are things that businesses pretty much make the living on. This notion of operational data. If you press A, then you can zoom. Really, the letter A? I'm gonna try it. You mean like that? No, I don't think so. See, for me, A is different because A switches between like all mode, and then slide mode. I mean, in the worst case, right, it's actually very easy. All we need to do is just put it up on like a new tab like that. Okay, so if you want, we can read it. Okay, cool. So I guess it's like this. You take like all the data that your businesses have and build this amazing thing called a data warehouse, like right there, and then start doing analytics on it. This is where you start doing data science pretty much on it, and machine learning, and then get hopefully some good insights. So I can skip the parts that we've done before. The main reason to do it is obviously to increase your profit. Okay, so it's easy. And then it went way back in the 1960s and 70s. People still wanted to know how the business was doing, but it was not that easy to tell. You got reams and reams of just numbers. But now it's on your phone. It can even be animating, streaming, interactive in real time. So that's quite a lot of progress. And then, wow, this is much smaller than, I apologize for this. Actually, wait, I'm going to try one more time. I'm just going to reload it because interesting things happen. Yeah, my JavaScript can do like very weird things. Okay, not this time. All right, I'm gonna fix it all. In the meanwhile, so there's two kinds of data, operational data and then decision support. Again, the idea would be that operational data are your small individual pieces of facts. And then you assemble them all together into one massive data warehouse. And then you call it decision support. And the big reason to do it is then everything is in one place. And then you can drill down as deep as you want and then get pretty specific insights. Or if somebody's too bored with that and say, I don't really want this low-level detail, give me a big picture, then you can go in the opposite direction. These are all attribute hierarchies, okay? Like, for example, how is one store doing? How is all of Western US doing? You can answer both those questions because you have all the data. Okay, so it's a pretty necessary, obvious, cool idea. It is looking towards the past, and then to interpolate, towards the future. And then we talked about all of this. I can skip. The main difference between day-to-day data and decision support data is this thing is all you're writing constantly all day long, and this is your reading all day long. So they're quite opposites from each other. And then here each is like fact after fact after fact. This is all like aggregated. So some pretty large differences, which is why they're both not the same. Okay, so this keeps bugging me because when I previewed this a while ago, this was all like normal size. It got like extremely tiny. So I'm still shocked that it's 100%. Sorry about that. All right, so we'll just go in the next step. These things all we looked at. The main thing is this notion of extract and transform and load. So load meaning actually create the warehouse. And extract is what do you want from the operational data. Maybe you don't want all the operational data. And then the transform is when you do things like filtering or maybe change all the date formats, currency formats into a single common format that you can analyze. All right, so there's entire companies, that do all this for a living. Then I said a data mart is a smaller piece of a data warehouse, almost like a single subject warehouse, where different departments in a big company like Amazon might want their own data mini marts. And then that way you don't have it all because you don't need it all. So it's a complementary idea of a data warehouse, still integrated. So a product manager for electronics can still tell how their business is doing, their aspect of the business is doing. And then these rules are all things that I went through. So we'll spend a little more time on the star schema, this so-called snowflake schema. A star just simply goes like this. Your actual facts are all in the middle. And then the idea is that every fact, meaning every sale that was made, can be described in terms of what product was sold, what time that sale took place, or what location the sale took place. So in that sense, the way you can describe every single sales receipt all those descriptions, the columns, they're simply called dimensions because it's almost like you have a multi-dimensional space, X dimension, Y dimension, Z dimension. And then all of these columns, these attributes are all pretty much like, access on those multi-dimensional space. And every single piece of little sales that happen would be one point on that multi-dimensional database. This little thing is worth like making a little illustration. Okay, I'm going to do it because data science, all that. In fact, even ML is pretty much like the same idea. So I'm just going to draw this for you. Okay, I'm just going to tell you that from now on, you start thinking about columns, see these columns, like that column, that column, that column, as if they are spatial dimensions. So now you have 3 dimensions. You can have a 4th dimension, 5th dimension, 6th dimension. They're all supposed to be 90 degrees from each other. The idea would be dimensions have values. For example, say time was time of the day. The store opens at 8 in the morning. Say 8, 9, 10 a.m., 11 noon, 1, 2, 3, 4. So every little thing is like a possibility, meaning a value for that time dimension. Product dimension, what are all the different kinds of products we sell? You can imagine that they're arranged in some kind of vertical column. And then the store locations can also be thought of as location ID, store number 1, 2, 3, 4. These are arbitrary, by the way. There's no rhyme or reason how you do it, but the fact is that you can do it. Then the idea would be that one single sale that took place, somebody walked into your store at 10 in the morning and then bought whatever this product was at that store. So I'm not able to do 3D, so I'll do it there. So a single sales receipt gave us those 3 pieces of information. That becomes a little dot. And then somebody in the afternoon went to a different store and bought something else. Then they would go over here. So the idea would be that every single sales receipt would become points like these, okay, in this multidimensional space. There's only 3D. Amazon can have up to 100 different things for every single thing that you make on Amazon Prime. 128, it's a nice number. That's how much, 100 plus things they know about every single transaction that they make. So then this is what can happen in that multidimensional space. Every single transaction all day long, it happens. And you can start to see patterns. You can say, wow, why are all these clustered? Like, in other words, how come so many people are going in the evening and buying that at that store? What is going on there? So you can go and actually find out some neat things about your data. That's the overall idea of this whole multidimensional analysis. And then you can slice it. You can say, just for that one product, just tell me what's going on, forget the other products. And then even for that one product, for that particular time of day, what is going on at all the store. So you can slice and dice, okay? And then you can zoom in, zoom out into each little attribute hierarchy. So that is really the overall big picture idea. Okay, so then the notion of a star happens because then it's as if all the sales that really took places in the middle and all those columns that are named like location, time, product, they're all like stars, they're points on a star, meaning the columns all go like all around. That's what this is. And again, the columns are called dimensions, okay? So dimensions, columns, attributes, they all mean the same thing. Okay. So that is eventually what you're utilizing in there. And then some of those columns, some of those attributes can form a hierarchy. For instance, location can always form a hierarchy because a location ID is just a store number, but the store happens to be in a certain city. Therefore, it's not just a store number, but it's also that city. And the city happens to be in a certain state. So it's not just the city, but also the state and so on. So you can, from just one single little piece of fact like a store ID, you can also derive, because that is happened, that's what's in the world, you can derive these extra attributes and make a hierarchy out of them. That is where Snowflake comes in. The thing that I just told you is right here. So all the stores in a certain city, even though they're individual stores, they're all part of that city. Then if someone says, tell me what happened in that city, I would go through every single sales receipt that I ever have and then look for that city name because I know it's the relationship that I already have. Because store IDs are what I really store. But then I know for every store ID what city it is. Then depending on whether it's a city that I want or not, I'll either include that sales receipt or exclude it. Then I can get everything from one city. Likewise, I can pick up everything in one state because again, IDs map to cities, cities map to states, and then region. So you can go up and down this and see how your business does. All right, so that's exactly what we just now said. Okay, so along this one dimension, imagine that even for time, even though I have a timestamp right now, 5:16 p.m., but then it's also, Wednesday. It's also still March, so it's got to be like the first quarter of the year, and so on. And the year is like 2021 is the 2020s decade, and so on. So you can form a hierarchy from out of anything at all. Say somebody buys a ream of paper, you can then call it office products. Then you can call it household products. You can call it small products, and so on. So you can think of columns for pretty much anything, and you can start to derive value from them. All right, so then the notion of a star, right? We already went through this. Again, the idea would be that if somebody, say there was a column here, a dimension here called location, and then there's a value called location, Los Angeles store 45. The store number 45 in Los Angeles can happen in tens of thousands of sales receipts. In that sense, it is a one-to-many mapping. So the one store ID can occur in many sales receipts. The one product ID can also occur in many sales receipts. So it's a many, one-to-many from all possible directions. So that is the idea. This time I'll use something a little different. I want to illustrate all this so we can draw like little quick pictures, okay? Like here. So then that notion of what I just now told you was actually a very easy one. You have the actual sales receipts in your warehouse like this. So then say this is the location column. So then what I just now said was location 4 can be here, can also be here, can be here, whatever. So therefore that is the location column. You have a separate column called location, meaning a separate dimension, and there are many locations. So 4 happens to be here. You know all about 4, all the other things about 4. But that 4 can happen in many different places. Likewise, you also have a product dimension, and so all kinds of products. And so maybe this is like paper products. So that paper product can be bought by, this person, can be bought by this person, can be bought by this person. So therefore, they're all one to many. All the ones, one row can participate in many rows in the main fact table. It's called the fact table. And then all the other dimensions go all around. So no wonder you call it some kind of crazy star, okay? It's like a star schema. So the star is made up of like all of these columns. But the reason why I put it up here to show you is this. A location called store ID 4 will also have extra columns that we can manually fill because we know where store number 4 is. This is where I can have a city column. And if store 4 happens to be in Los Angeles, I'm going to say LA. And if store 8 also happens to be in LA, I'm going to say LA. If store 20 happens to be in Santa Barbara, I'm going to say Santa Barbara, and so on. Likewise, I can have a state column. And then because all these cities are named, they're all in California, the state column, I can manually go and add California. So these extra columns are all coming just from that one column, okay? It's very interesting. In that sense, it's almost like a primary key. And the primary key is the only thing that goes here. So through that, you can know all the other things. This is why I told you if the product manager says, how are we doing in California? Then all I need to do is take every single location ID, go in here, and see which one of them says California, okay? So that's pretty cool that we can do that. So these, as you can notice, are highly denormalized, meaning they're not broken up. It's all in one. So when you have everything completely denormalized, so then again for the time stamp, 8 in the morning might also be called morning. And say it happened on Monday, it might be called first day of the week. It might be called March. You can get all that just from today's date. So in that sense, the whole hierarchy is all denormalized. So when you have everything denormalized, the whole column, the whole dimension is denormalized. That is when you have a so-called star schema. Meaning there's no hierarchy. It doesn't keep going. There's only one level of star. So the star is like this. That has everything that you ever need to know about it. It's all in one place. Very denormalized, like lots of data, okay? And then a single cells can like point to like all those. In fact, it's the other way around. One of them can point to many cells. They all can all point to many cells. Again, it's one to many. One to many. Okay, so that is what a star was. And so then we can easily extend the star to a snowflake because then we stop saying to the star, don't have the whole hierarchy all to yourself. Let's actually break it up in like little pieces. See, what I just now told you is here. So the sales is still sales. The one sales, the primary key called location ID, tells you what location it is. But that additionally can also tell you about states and regions and cities and everything else. So in that sense, these are highly denormalized. Highly denormalized in a star. Then the next evolution up from here is to say, these should all be their own columns. There should be a little mapping between any two of these, any two of these, any two of these. This little hierarchy of tables. Then you call it a snowflake because it's almost like a fractal star. All right, so the fact table is in the middle, denormalized is like over here, and then another representation. This is Wikipedia. And dimensions are those extra columns on the side. Okay, so dimensions provide additional perspectives. So those are the additional perspectives. In other words, the sales receipt only told me location ID 40. But now I know 40 is also part of California. So if somebody ever says, tell me about California, I'm going to include 40. So it is additional perspectives, okay? So fact is just a fact, but now we can do more with that fact because we know more about what characterizes that fact, meaning what columns went into describing the fact. And so that is where the hierarchy comes in. You have an attribute hierarchy. All right, therefore, this is the diagram that I do in multidimensional space. Every dot, every transaction that happened is one little dot. So suppose somebody went during this time to that store, and then bought whatever this middle product is, that little dot would go there. Say 100 people all went in the same location, bought the same product at the same time. Then all those dot, 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 dot would go in the Rubik's Cube. Think of this like Rubik's Cube. In the one little cube there, so all the dots would appear. They look clustered. On the other hand, if somebody bought stuff here, somebody bought stuff here, and what. So therefore, the whole cube, even though only 3 dimensions, can literally have a billion different points because a billion different transactions took place. And now imagine the cube having more than 3 dimensions, having 20 dimensions. All that a dimension means, the person that went and bought this, what is the age? What is the race, believe it or not? Or what part of the city do they live in? And what do you think the income is? What is the education level? So people like Amazon, they know all of this about us. So you just you just order something and you take it home. But then they put you in that 100-dimensional space as one dot. That's crazy, right? So this is where analytics starts to come in. All right, so this I told you can go up and down, meaning I can ask for my information at any level. Rolling up means a big picture for all of Western US, how is shoe sales. And then the opposite is drilling down like a microscope, just go zooming in and tell me in that one store what happened. We're hearing bad things about the store, tell me what happened. Well, so then like I just told you, in a Snowflake, all you do is keep the location ID just atomic. You only point from that to city ID. So then that is like a table where there are many locations and then they all basically have the same city, right? But then the city is in a separate table. The city has a city ID, you only store the ID. And they say, what is city ID 25? Oh, city ID 25 is San Diego. All right. So then that same San Diego can occur in many locations, meaning there are many stores in San Diego, and all those stores can occur in many sales receipts. So it's a very cool one-to-many hierarchy. There's a whole one-to-many hierarchies. Likewise, the state of California has many cities, not just San Diego, and they'll all say California, the state ID. And then Western US has not just California, but also Oregon and Washington. And so then a region ID called like one for the West would have 3 different states in it. So it just goes on like that, okay, like a hierarchy. We simply broke up the star, the points of the star, and made them into a fractal. So rather than just a one star now, a star is more like a star of a star. So now we can start to do this. We can actually go in each one of those points in the star and then store some additional information at that level. So it's like this. At first we had just the star, and then we had the table here. But now we break that. So all this used to be in one table. So now we break it up and actually make it into more tables, right, like this. But then you can also then add something extra, like just at the city level. For every single city, I can store the population of the city or the tax bracket or something, the sales tax that you pay. All that can be stored as part of the city. So we can use this fractal to advantage. We can have more facts that characterize the sale that just took place at that level. Meaning the single sales receipt can tell me a lot more at the location, the store ID level, can tell me a lot more about this at the city level, the state level, and also at the region level. So imagine they're all doing that, okay? So now you call it a fractal, just call it loosely fractal. Because roughly the idea would be that it's as if this is also like a little, star like that, and then it happens to have its own dimensions. In reality, the star is not multiple, there's only one of them, okay? In other words, rather than go like this, you only pick like one of them. You still call it a fractal, it's a snowflake. Awesome. So that's all that was. And so, just simply normalize it. Now it's not denormalized. This dimension table that used to be denormalized is now heavily normalized. Normalized will break it up, right? Therefore, dimensions can have their own dimensions. That's all we're saying ultimately. In that sense, a dimension looks like a sales thing, like a fact table, because a fact table has dimensions. But now a dimension can have another dimension. This means now the navigation is going to be a little slower. You have to join all the tables. And then that's the Wikipedia representation. Just keep going. All right, so forget the 5. There are basically 4 ways in which you can organize all this data, okay? So I've shown you 2 ways. The first way is facts just go in the middle, and then you have highly denormalized, meaning all the whole hierarchy. It's all just in one level. You call it a star. Then the second is you go from a star to a snowflake. So star was a fact will foreign keys, like a location ID, would point to a single level of dimension. So dimensions don't have their own dimensions. But now dimensions can have their own dimensions. So these are 2 what we just now talked about. The third way you can organize this information is, I brought this up last time, I don't know if you remember, is you don't need the star or the snowflake. You can throw both of those away. Instead, you can take all the information that you meant to keep in the star or the snowflake and put it all right here. So I think I drew the diagram, so I'm going to do it. Do it again. Yeah. So what I mean is, imagine there was no snowflake or the star. That's what you can do. So you can add extra information right here. So why not, sorry, not in this one, in here. So you go in the main sale, the fact table, just start adding all kinds of extra columns. Just like a location column, you can have a city ID column, state ID column, region column. And then for a product category, why just have a product ID, but also have all kinds of product categories column? Is it groceries? Is it, big? Everything that you meant to keep in all these points, like all over, take all of those columns and put it all in here and say, I don't need the snowflake or the star. Heavily denormalized, lots and lots of info, but everything is in one place. So you can zoom up and down because it is all here. And you derived all of these just from those. So those things gave you even more information. From the customer ID, I have all kinds of customer information that I can store. Lots of duplication, right? If I buy something 100 times, then my ID is going to show up here 100 times, but that's totally okay. I told you it's denormalized. And so, but all in one, so people like it. Right, exactly, that is correct. See, in fact, this is 1NF, correct. So then what we did was go from 1NF to 2NF to 3NF, so to speak, and now we're going backwards, just to keep it on one plane. So Snowflake is as normalized as it gets, and then this is as denormalized as it gets. So this is my version 3, okay? So my third possibility was like right here. Oh my gosh, sorry, wrong part of the slide. All right, so then the thing that I just now told you was star, snowflake, and this one. The fact table can be supplanted. Extra columns can be added from the star or the snowflake. Then you don't need the star or the snowflake. Then you can take that and then do something crazy with it, which is make many copies of these, but then one copy for each level. In other words, from 3, you can go to 4. So how do we do that? Let's draw that. Just keep having fun with all these little drawing tools, okay? So just now what I told you was this. I said you can take your fact table, your sales receipt, which only happens to have the store ID. You can, by the way, look at your sales receipt next time. It'll tell you store number 45. It'll actually tell you stuff like that. So we had that, right? But now what I just now told you in here was can be supplanted. It means I can then take this and add extra things like a city ID, state ID, region ID, time of day, week, quarter. I can add all that. So now this has lots and lots and lots of columns, but everything is in one place. Then we don't need the star, snowflake, all of that. But then now you can do something different with it. Rather than adding a location ID right here, along with, sorry, there's a store ID. This is store ID, right? Store ID. And also a city ID. But instead you can do something different. Because with this, what will happen is store 45 would say LA. Store 27 would also say LA. Store 60 would say LA, and so on. And then likewise, many cities all would say California. So California is going to be repeated even more times. So too much duplication. But instead, don't do it here. So make a completely separate table just for one of those cities. So just for LA, take all the store IDs that are part of LA, right? And then put them instead of store ID, just even leave it out because you're making an LA version of all of this. So I'll have a separate fact table just for Los Angeles, a separate fact table just for San Diego, a separate one just for Santa Barbara. So therefore, I can make multiple versions of these. That's what this is. A separate for each attribute. Okay. So for each of those hierarchical attributes, I can make one, like already rolled up, so to speak. Likewise, I can make a whole fact table just for California. I can make a whole fact table just for Washington. And that is only one of those dimensions, the location dimension. Likewise, I can make a whole fact table from all of these just for 8 a.m. I can make one more for 9 a.m., one more for, the month of April, what. That's crazy, right? So I can start with one fact table and make all these crazy variations because it's what all the sales managers want. It is practical, absolutely. You're just wasting so much disk space and you're doing some pre-processing. But the analysis is amazingly fast because you've pre-done all the work. There's no joining, nothing. Not even looking through all of this in the SQL. Exactly whatever you're looking for, I already have your data at the expense of a ton of disk space duplication. In case where they're using multiple fact tables to have, right, that's a great question. Okay, that is simply a design choice. So for any one of these, right, say take for California, do you fold everything else in? Or would California have like separate dimensions for the other dimensions? Meaning, would you still have a separate product table? And would you still have a separate, time table and so on? You can pick whichever you want, okay? That's a great question. That's a design choice. I mean, the one that says you can have everything all in one place. crazy amount of duplication. That is like multiplying every possible value for every attribute and make that many rows. It's just a crazy, incredible amount of duplication. But we don't mind though, because you're just writing some blind SQL to go from here to there. You'll end up with a massively large table, but the table has everything you can possibly need. Primary keyed on the main thing you're looking for. Like I always like to do analysis city by city. Well, I can now give you a fact for every single city. Start with that, and then do all the extra stuff just by going into it. Okay, so I think you guys get it. Okay, that's number 4. So number 3 and number 4 are very similar. The only difference is in number 3 you put it on in one place. In number 4 you make multiple parts of it at different levels of aggregation, meaning from the zoomed into the zoomed out. They're all different. Cool. Okay, so what else can we do? Okay, good. Yeah, then what does denormalizing mean? I already told you, okay? Just simply add all the extra, like start with the location ID, which you already have, but also add things like city ID, state ID. It's all redundant data over and over, but it's fast queries because it's not clean design, but we don't care about designs. So this exactly what I told you, this thing in here. Again, this is being described over here. Same idea. You can now have rolled up versions of them, okay? You can have multiple fact tables because there's only one fact table that you really have. But now you can have a so-called, not just sales, but sales city, and also a sales location and so on. Okay, sales state, sales region. So you can take the one real fact table, my pile of receipts, and then make all these artificial versions of them. It's also a different way to denormalize, but still each of those pieces are, yeah, they're denormalized exactly. All right. So you can read this, all right? It just tells you what I told you. Fact table is always in the middle, and fact table by definition would have everything that the sales receipt had. You cannot help it because so the sales was. But then now you can start to break it up in dimensions. But then if you leave it as a star, the star is also denormalized too much at one place. But now you can start to break up those dimensions. Then you can have snowflake, I told you. And then the fact table is always denormalized, but you can denormalize it even more by piling on all of these onto the fact table. That's what that is. Okay, so then snowflake analysis. Oh yeah, I told you all this. Yeah, so at every level of the snowflake, you can add extra information just to make it meaningful. Otherwise, the snowflake is pretty boring. You're just pointing from table to table. Then you think, why even do that? You can make it useful by putting something for that level at that level. Okay. And then, yeah, then this finally what I told you. The reason to have a snowflake, first of all, is you want analysis done at multiple levels of your attribute. Your attribute is hierarchical. But now you can make hierarchical fact tables and then throw those attributes away. So no star, no snowflake. Again, too many ways of saying the same thing, many words. But if you read it, you'll understand. All right. Okay, so BI, all this. And then, yeah, again, this is ultimately what you're doing. A single Amazon purchase order can have so many dimensions, up to 100 dimensions. And then, they can be groups. It's called hierarchical clustering if you know about data mining, okay? You can mine data, but then you can cluster clusters. So we'll get to all that in upcoming weeks, I promise. Yeah, so everything I told you is all here, okay? So take your time to read it. And then, so now you constructed, all these cool tables, right? Fact tables, normalized, denormalized, it doesn't matter. You have everything that you ever need for doing analysis. So what does analysis mean? That's what this means. Just simply, just stuff like clustering or machine learning or linear regression, or basically any kind of, data mining algorithm you're trying to run on. Decision trees, like all of those you get. And then the whole point is you're trying to explain the past. So the sales manager says, why did our sales go down 5% every year? So at this rate, we're going to go to 0 in 2 years. What happened? Like, how are you going to explain it to me? Then you can say, like this really, started slowly, but we didn't notice it. You can just go back and see what happened, okay? That is called explanatory. It's focused on the past. So that is useful to, find out like why we screwed up. But most of the managers want to say, what is going to happen next year? If all else remains the same, are we going to grow linearly? We're going to just take off like a rocket? We're going to flatten out? Even worse, are we going to drop? That is looking towards the future. We call that predictive analytics. So past, future, obviously, two different reasons. This already happened. There's nothing you can do, but you can hopefully learn from it and hopefully not screw up again. This is about, how are we going to do? Like, should I keep the store open? Should I hire more people? Should I, diversify my product, inventory or whatever? Cool. So in the end, past and future. And then we call this whole idea OLAP, okay? The word online just means nothing. It just means warehouse. So warehouse processing, the whole big data processing is called OLAP. That's really all it is. It's not advanced really. Yeah, I said it's multidimensional because every attribute, every column is no one dimension. And so that's it. I don't know what all this means. Yeah, this dashboard. So then, some sales manager can watch like numbers on a dashboard, just animate, just like that. These things were all said before. So now the part that I'm telling you is this part, okay? So after you do the whole Snowflake, and star, that's all over here, and you start doing a data mining, analysis algorithms for these reasons. You can produce like all kinds of reports. Now it's on your phone. Okay, all that part. So nothing new there really. And then when you have data marts, it's the same idea, but now think of this as mini warehouses, So you have this big, massive warehouse like right there. But then from there, you extract them into little pieces. In other words, the manufacturing department says, we want our own mini warehouse. That's what this is. So then they have their own UI, the tools for it. Likewise, the marketing people say, I just want marketing figures, and the sales people want sales figures. So R&D, purchasing. Everybody has their own pieces of the data warehouse. And the reason is efficiency. Then, because somebody that's purchasing couldn't care less about what happens after the product is manufactured. Input, output. Oops. So these are diametrically opposite. So maybe there's a reason why you want to keep it like that, okay? Or we're just saying the same thing. So don't pay any extra attention to all that. They're just like explaining what I told you. All right, so then the thing that we just now said, how do you build this table? So this table so far, it's been a little abstract. It could be anything, right? This little cube can be abstract. Although the diagrams I drew made it seem like it could be tables with primary keys and foreign keys after all. If you do that, actually use Oracle, and then even for your homework possibly, and then do nothing but just relational SQL and do this kind of data mining. Then we call it ROLAP, relational OLAP. Standard relational databases. This means SQL. Do everything with SQL. You add 2 extra keywords to SQL when you group by. You can say group by cube, group by rollup, and I have examples pretty soon, hopefully in the next slide, I think. So that's that. On the other hand, you can just throw entirely all of this away, meaning no SQL, no Oracle, no nothing, no relational database, no what. Instead, pretend that you have a multidimensional C++ array. Okay, C++ just because you've got pointer memory. You can build your own machines out of nothing. You can buy like a whole ton of RAM and disk space, and then write some custom architecture. You can even do an FPGA chip or something if you want, just for this kind of data access, and then entirely do it all yourself. So you have this, you literally build, this data warehouse yourself, okay? But then you're writing all the code to actually store all this data in these multiple dimensions. These are things we don't need to go through. Already done that. So that, again, one sales fact. It's all just going into some point in this right there. But this multi-dimension, here's only 3 dimension, but what about 100? It's as if you allocated a massive amount of memory, a pointer to a massive amount of memory, where each dimension is just like, that pointer. And the next dimension starts over here. And the next dimension starts over here. And within each dimension, like all those little slots, they're all like subslot, whatever. So you got pointers for everything ultimately. But in reality, obviously, memory is one long sequence, right? So you got a pointer to a pointer to a pointer. In other words, a one-dimensional pointer is just simply that. So you can point to a block of data, and that is just a star. So then you have, again, this block of data right underneath, and so you have a star for that. These 2 stars can be pointed by a pointer to a pointer, where it's pointing to that, pointing to that. So say you have a bunch of pointers to pointers like that, like that, and then that's pointing, that's pointing. So then these pointers to pointers can be pointed by a pointer to a pointer to a pointer. So then this is ultimately the whole table. So you can hierarchically do this crazy cool C++ allocation. In reality, the whole thing is one massively long memory, but now it behaves like a multi-dimensional table. You write entirely the code for all of that, okay? You can even do hardware, custom hardware. That is called MOLAP. So there's a bunch of, businesses that do exactly that. These are hardcore, like Unix, C++ people that say everything else is slower. I don't want SQL. I don't want, weird like keywords. Just give me like raw hardware, raw, operating system. I'll do it myself. That is what MOLAP is. You can again look into that if you're fascinated by it. It says uses proprietary techniques to store data in matrix like n-dimensional arrays. So this is where the whole C++ analogy came in. Pointers to pointers to pointers to pointers to pointers. Basically a 100-dimensional pointer. You probably never done that in your life, but it's possible. I do lots of image processing and also volume like voxel processing. So the most I've done is star, star, star. What is a pointer to a pointer to a pointer, meaning I can get to any XYZ location in space. But now imagine having 100 stars. It's pretty funny that your compiler might even actually compile it, right? Try it. That is what this is ultimately, at least in principle. Yeah, then you can just grow the n dimensions. They become hyper. Hyper means more than 3D, any number of dimensions. Just call them dimensions. Cool. That's MOLAP, okay? Very different from ProLab. And then this picture just tells you what we already said. Just a star schema, medium to large. You just ignore all this. This is the main difference. Data cubes, custom built data cubes. Yeah, okay. And it's all proprietary. You write your own C++ for it. Right. The biggest reason why you would even do that, like why not just use SQL, is because if your data gets massively large, there's nothing, this is as fast as it'll ever get. It's raw pointer-based block memory. And so then you just write the code to do all the analysis blazingly fast. People pay for this. Do MOLAP. Okay. Like this, right? What if I actually told you custom MOLAP architecture? Like that. It's a research topic as well. I like that. There's even a whole lot. It's like a whole bunch of them. Yeah. You can actually see like what this looks like. Right. Till then, the same things that I tell you would be over here, okay, like that. So yeah, this is like 3D again, the whole slicing and dicing idea, but you can do it in any number of dimensions. In 100 dimensions, slice away the 100th dimension, you have a 99 dimension cube. Slice it one more time in a 98 dimension cube, and so on and on and on. Just go up and down. I told you. All right. Yeah, now I can tell you the whole SQL stuff. And this is a very easy little thing to tell you, which is this all the SQL that you know already. But now if I give you a warehouse table, say I give you a Snowflake schema or a star schema, then how would you add up like all the columns for me along one dimension? In other words, say I have sales in my hardware store. I sell many different kinds of products, and each product has a product ID. Likewise, I have sales going on for many months, like all of last year. So what if I said to you, first start with the month for last year and tell me everything that happened in January, then February, then March, then April, then May. And within each month, tell me all the different products for that month. And then for the month, how much sales took place. Next month, how much sales took place. If I add all those months, I would know exactly how much I sold, product last year. Then that is called a roll-up. In a cube, it is in a roll-up, first of all, going back to what I told you, the main way you organize information in the month followed by product idea is by month. So January, February, March, and then within each month, just all the products. But now what if you could do it by month and by product as two sets of values, but both add up to the same sales anyway, basically how much is sold last year. That is called a cube relation, where on the one hand, I would do exactly what I did before, like roll up every month, I'm gonna know like what product. But now additionally, for every product, for every month, how much did I sell? Just for the one product. Next product, what? Then I add those numbers, and obviously I'm going to get the same numbers as before. That is called cube. So cube means all columns that you name roll up is n minus 1 columns. All the columns that you name except the last column, okay? So in general is n dimensional, but I'm going to have n be equal to 2. It's pretty easy to illustrate. So just for two columns, such as month and product, what can we do? Rollup says, name all those columns, such as month, product, in sequence. So then the very last thing that you name, the nth column that you name, there's no total for that. But then it's grouped by all the other columns. In other words, you're slicing and dicing by all the other columns until you get to the last column. You don't slice and dice the last column. Here you slice and dice it in multiple different ways, is what you're saying. You first slice by one column, and then give the whole aggregate for the column. Then take the warehouse again, cut it in a different column, and take the whole aggregate. Cut it by now a third column, get the aggregate. So keep getting aggregates over and over. Here it's more like hierarchical, okay? So a very big difference between them. Just one keyword difference is all. Now I'll actually magnify it, is worth looking at it. Okay, so what we say is pretty simple. The syntax is exact same thing. Select a bunch of columns, from a table, bunch of tables, where the condition that I want, group by roll up, and a certain bunch of columns. And then having is further to restrict that. You already know that. Ordering is a visual ordering. The main thing is group by roll up, column 1, column 2, column 3. This is going to be the first column to cut, second column to cut, third column to cut. Last column will not be cut, like this. So group by roll up, vendor code, product code. It means per vendor, all the products, how much sells, say for some time period, or maybe forever. Next vendor, only 2 products bought. That is the subtotal. Next vendor, only 1 product bought. That's the subtotal. next vendor, next vendor. It doesn't matter what product, sorry, because you're not slicing and dicing along the dimension at all. And then you add all of those. This is how much we bought from all the vendors for all the products. Okay, so remember the number, okay, 20 to 50 to 06. But now you can do the exact same thing as a cube calculation, in which case you can get it two different ways. So this one, the thing that I showed you was subtotal for each vendor because we named the vendors first, all products. We didn't slice along the product category. The sum of just only the subtotals, meaning only vendors. But you change the one word from roll up to cube, then now you get two different ways, okay? So in cube extension, literally, that is the only change. It's all the same as before. Everything is same as before. One keyword change. But now you get it two different ways, okay? By the way, the example changed a little bit. Now it is month and product, not vendor and product. In any case, first of all, you get month, month. It doesn't matter what product, total, total. You add those, you get that. Then you go back and do it the other way around. For every product, both months, like a 9 and 10. Next product, 9 and 10. Next product, 9 and 10. So now it's by product. This was by month, that's by product. They both become equally represented. So in a cube, it doesn't matter how many dimensions you name, in what order you name them. You will get a subtotal for every single separate column. And obviously, all the subtotals will add up to the same main total. Very cool, right? So in here, you're literally taking the same warehouse over and over and slicing it one at a time along multiple dimensions, as many as possible. Whereas previously in rollup, you're doing a hierarchy. You're first cutting by one and taking that and possibly cutting again, and then have a subtotal. The very last column will not have a subtotal. It can't. Cool, because there's nothing to add up. Huh. All right, so that was the last idea. This is pretty neat, okay? Many SQL systems support that, like Oracle, SQL Server. You can try it at some point. And this is how the world of SQL warehousing works. They pay you a ton of money for this. But that said, this notion of ingesting data once in a while and doing something cool with it is slowly going away. What does that mean? It's going away because this notion of extract, transform, load, it's a periodic batch process. It's called batch loading. You set it up for once a day, once a month, even like once every 6 months. The business is pretty slow. But these days, internet business runs in real time. People want to know last half an hour what happened. They want to decrease the price. People are not buying something last half an hour. Can I change the price now? Like, tell me. So you need to know what happened last half an hour, not 2 days ago. Therefore, you don't even do ETL at all. You dump your entire fact tables, no ETL, no aggregation, into what's called a data lake, okay? So data lake is, and you can make it streaming, so it's really real-time data. So anytime a sales receipt, goes through Ralph's, they can take the data and dump it into a data lake. So it's a continuous form of analytics. And as soon as a piece of data gets dumped on a data lake, you can run off some calculation. Or maybe the calculations can pull the data like every few minutes and get data out of there. So you can set up some kind of meta continuous way. It doesn't mean real-time continuous, but constant, never stops. So analytics is constantly changing. Wow. And the reason for that is lots of unstructured data, streaming data, cloud storage, all of these. So these things all together make it possible to not have to do traditional ETL anymore. People think this is too slow. Like my business is basically already screwed. If you tell me what happened 6 months ago, I don't need to know it. I need to know it ongoing, constantly. So that definition, that kind of product is called data lake, okay? Okay, so again, you can Google all of this. It's pretty fascinating. Data lake, okay, versus data warehouse, okay? In fact, that's the very first thing that came up. I didn't even search for it, just autofill. You see it. People will tell you like all the differences. What is a warehouse, Again, if you want some summary of what I told you, you can find it in many different ways. Okay, but the key point is what I told you. It's because of all these NoSQL databases we'll talk about and all the cloud stuff. This all makes it possible. In fact, those exact 4 things I just now told you: cloud, and then cloud storage, cloud streaming, cloud processing. Just send it all to a Kubernetes Docker container that is running on AWS that you pay for. They can do all the work and send you little pictures, and then you'll see how your business is doing. OMG. So no more warehousing. That's really the future. And then there's also something called reverse ETL, which is also fascinating. So please read up on this, okay? Just Google it. Yeah. So there's people never stop, by the way. There's ELT as opposed to ETL. I might put up some of these links on extra so you can read about them. These are cool. This is really what is happening. So you should not think that the warehouse is really, like a cutting edge thing. It is slowly but surely not. Okay. Good. All right, so we got caught up into very modern stuff, and I'll find you some links for it, okay? This is really what gave rise to data science, believe it or not. All this kind of calculation. People said, wow, we should do more of this. Since we did the, no, well, not. I'll literally only ask you what I remember telling you last week. So nothing that we talked about today would show up on it, okay? So don't worry about it. All right. So without missing a beat, it is. It's not that the streaming real-time analytics that we do is ignoring the past. You can include the past and also current stuff. It's like a constant monotonic increase, okay? You're just adding more and more and more, but in real time. So yeah, you definitely should not think that the past is gone. It is more like we're still doing warehousing, but not every fixed amount of time, but more like pretty much continuously, as continuously as you can afford it. Really, that's the truth. Yeah. So it's still warehousing for sure. Okay. Because again, to extrapolate, right? You cannot just take today's half an hour of data and say, how is my business going to do in the next 5 years? If you knew 50 years worth of data, that's a much better extrapolation than just looking like what happened last half an hour. That'll highly mislead you. Again, it's a lot like stocks. The long run, your stock might actually go up if you do nothing and just forget about it. Look at it after 10 years. But every day you zoom in, it's going to be like micro fluctuations. Sometimes it might even do that. You shouldn't have a heart attack, okay? Because gradually it'll go up. It's the same idea. So you cannot just look at instantaneous, data. It'll mislead you. Will the energy and appreciation be factored? Yeah, definitely. This is a very good question. Yeah, you can add so much extra calculation in your SQL to say that the older your sales were, for example, based on the timestamp, the lesser its weight. So you can factor depreciation into it. Absolutely. And then if you're asking about the actual energy that is used up by the warehouse, that is also definitely a different thing altogether. That is the whole cloud energy usage. That is why people like Amazon, they go to the San Bernardino desert here in California and build these massive data centers. And so then they, buy electricity from the city. The city is happy to sell them electricity. So somebody's, paying for so much energy to be used, if that's what you're asking, for all this calculation to happen. But yeah, they're both two very different answers. But yes, you can build all that into your analysis for sure. Okay, cool. I think that's a really good segue into a very different world altogether. So slowly but surely, it is almost like a halfway point. So it's going to take us from the world of tables, entities, primary keys, foreign keys, normalization, SQL, to something that is not quite all of that. Like in your homework even, I'm going to actually have you do the homework as what is called HTML5 local storage. So on your browser, you can actually store data. It's called local storage. And so the local storage API, this API in JavaScript, is going to go somewhere in your hard disk and store any data that you provide through JavaScript as key value pairs. So there's no table, there's no relation, nothing. And I can then go and do analysis on the values that I store. If the values I store are spatial data, like actual XYZ points in space, I can say what is the overall area of area of all the locations. So I have ... then tell me the overall actual square miles. No tables whatsoever. So that is what is so cool about things like spatial data. Gradually, we don't need tables at all, okay? But you can put them in tables for sure. So I'm going to tell you all this. A spatial database, taking it from the top, like what is a spatial database? What characterizes it? In other words, how do you define it? What's in it? And then why do you need it? So the best part is, why do you need it? And then how do you create it? Just to cut to the chase, okay, it is all very simple. It's right here. Maybe these three. But really those two. What we're doing is something so simple. As it comes out of the box, a standard relational database has very simple column types. All the column types that you used in your SQL homework. So those column types are not enough to do like so many other types of calculations in the world. In other words, any single relational column, just Oracle, if you install it, it's only going to make the column be Boolean, can be a date, can be like a number, can be a string. That's really pretty much it. So simple. What if I want to store a vector? So suppose I'm launching quadcopters all day long, right? I actually want to store real XYZ vector values in the world. I want to store the location XYZ. So I think of a vector as XYZ. But right now I have no way to do it. There's the whole notion of, like compound attributes, right? So I can obviously take three of them, three columns, the numbers, and then I can call one of them VX, VY, VZ. And then that value I can actually store in this row. In other words, I can fake it by, it's what you do in C language, right? You could make a struct or something that's actually no object. You can use loose columns to, do it. But the problem with that is, suppose I then want to take the dot product between this vector and that vector. A dot product is a cool little operation. A dot product is simply, this x times that x plus this times y times that y plus this z times that z. I would like a nice little dot operation if possible, where I can have v1, dot v2. In other words, it's a nice little method that I would like to have. But here there's no methods at all. I need to read this row XYZ, I need to read XYZ, and do the multiplication by hand myself, okay? Like C programming. We don't want that. So thankfully, all databases give you a way to write your own custom class. You can actually make a class vector. You can do this in C++, right? Curly brace. And then you can have private members XYZ, like double XYZ. Then you can have public methods. You can have methods. And the methods are where you'll have a dot method. And that is why, if you already know your XYZ, say a new vector is coming called V2, then the return would be x times v2.x plus y times v2.y plus z times v2.z. Return that. Likewise, you can do a cross product. For that, you would have an I, j, k here, and then write v1 and write v2, and pretty much do a determinant calculation, right? So in other words, it is I times this little mini subdeterminant minus j times that product, and then plus k times that little submatrix. Then you'll have my ijk. In other words, I can do a cross product between any two vectors and make a little cross product. That is all cool to have, those methods like dot cross, or how do you want to unitize, normalize a vector, all of that. Thankfully, relational databases make it possible to write your own classes. Then once you make a vector class, it still would have XYZ, but then now the system calls this a vector type. You can make a vector column and store like a dot x dot y dot z. Then I can take two of those vectors and literally do a dot product. So I can augment the language with my own operators, those are the operators, with my own data types. So these are the data types, which you can just call it data. And then the operators, we call them methods, okay? So the whole point is that methods would operate on data. Cool. Suppose my data was all color, I'm storing like object colors, then one of the methods might be invert the colors, like literally do 255 minus R, 255 minus G, 255 minus B, get the complement color, or increase the color contrast or make it desaturated. I can have any number of methods. So the whole point is members and methods go together. That is exactly what we do in spatial. In spatial, I can make a class here called point, and make a point class. I can have two members called latitude and longitude. Now it starts to get pretty interesting. I can make now a point column, and then I can have a name for a point column. The name might be Tommy Trojan, and the point might have a latitude longitude value. I can look at my Google Maps and type exactly where Tommy Trojan is. I can have a name called Levy Library, and I can put in the Levy Library location. I can have a name called CS Department, and I can have a XY for it. Then I can ask from Tommy Trojan, which one is closer, Levy Library or CS Department? I don't need to do my own calculation. There's already a distance function built into the spatial operator. Distance between Tommy and Levy, distance between Tommy and CS. I'll just take the min of them. So cool. In other words, we're doing operations on spatial data. So the previous example I gave you, suppose I give you so many points, all as latitude, longitude. You do a very cool operation called a convex hull, which is make a convex polygon that surrounds like all of them. And then you can ask what is the area for the convex hull. You don't write the calculation yourself, it does it for you. It triangulates all of them and adds all the triangle areas. Or you can find the centroid. You can say for all the dots that I named, what is the centroid? I can go to random spots at USC, or maybe find all the USC library locations. Then I can ask you to write a little thing in SQL that says, output me the centroid. Like where should I have to stand? So make equidistant on the average from like all the libraries. You don't have to manually add anything and divide by n, okay? That is all the notion of a spatial operator. So that is really what spatial data is. It's pretty much like a library, an extra library that you add, a DLL that you download sometimes and put it in your system somewhere. Then it allows you to make point types where each point is latitude, longitude. It allows you to make line types. A line is an array of points. So now you can store a whole array. So say I started the Jefferson Gate and then wind my way all the way and down, go to the Exposition Gate. I can stop all the way midway and actually take like sample some data and take all of the data and store them as x, y, x, y, x, y. I'm storing an array of them. We call it the line data type. A line is made up of a bunch of points, okay? Then I can ask, what is the overall length of the line? I don't need to do any Euclidean calculation. It'll tell me. What is the length of the 10 freeway? Wow. All the way from Santa Monica, wherever the heck it ends in Florida, it'll tell you 3,000 miles. So it gets extremely cool, these operations, when you pair them with data types. So point is a massively cool data type. Line is also a cool data type. The third main data type is just simply a polygon. So a polygon is again exactly what you think it is. Now it's a series of points, but it encloses an area. Say I have a building somewhere. Say the CS department building roughly looks like this, okay? So now what I can do is I can take all of these points, XY locations, take my GPS, my phone, just look at it, and then type it all and make it a polygon type. And then I can say, what is the area of that one polygon? It'll then find the area of this and tell me what the area is. So cool, right? These are exactly what I'm going to tell you now. Just simply 3 new data types, although there's many more. You can have a curvy version of this point that's called an arc type. You can make it more continuous. Say there's a golf course, that looks like that. Golf course is not just straight lines. So then I can make it be a little bit curvy. Or my polygon is again, sometimes that's what I just told you. A road might not be choppy like that. A road might be nicely curvy, a windy road like that. And so now I can make that. But it all goes down to just those basics, okay? Points, lines, and polygons. And points can be not just 2D, you can even make 3D, 4D points. Astronomers can actually cluster galaxy data by storing XYZ values to them. And you can do cosmological level calculations. What is the volume of the Milky Way from, what we can measure it? Wow, millions of cubic miles. Cool, right? We can do that. Indexing, I might as well tell you here. Indexing is when you have like lots and lots of points somewhere. How come I'm able to go to Google Maps and so easily scroll with my fingers? And how is the map updating so fast? Because the answer is indexing all the data. Just like you can index standard columns and then very quickly get you some search value. When you are swiping, it knows your location. Google Maps knows your location. So it's only loading tiles near you because it took the whole world and segmented the world and stored them as different rectangles. So depending on where some user is, they're here, they're wherever, then you take that user's location and only give them their data. So that is the notion of spatial indexing. So spatial data can also be indexed. That's a cool little topic right there. Wow, now you know the basics of everything. We can stop. That's this. And then implementations and like extra cool stuff. All right, so a spatial database is just very simply database that stores spatial objects. If I store money, GPA, or how somebody feels every morning on a scale of 1 to 5, that is not spatial data. Spatial data must include at least a point. It means you can at least be a dot somewhere in the world, or possibly a line. You have like a length. It's not just a point. And then you can be a polygon. You can be an area. Unless it includes these, it is not a spatial database. That's pretty simple, but that's what it is. So you have to have a spatial location, which is a point at the least. Extent means a line or in the area, which is nice to have. All right, so that is all a spatial data is. So that means galaxy clusters are spatial data. But spatial data that is related to Earth, because we all live in the Earth, is very special. So we call it geospatial. Geo means Earth. Political borders, okay? So where are our nuclear power plants? Where are submarines located all around the ocean? Where are North Korea's missiles? All that is geospatial data, believe it or not. So governments take all this stuff extremely seriously because warfare at one level, at one level of analysis is really all about spatial data. Where are the enemies? Where are the weapons? Where are all soldiers? Where's the boundary? What did we gain? What did we lose? All just spatial data. So extremely fascinating. If you like spherical trigonometry, right? Distance calculations on like a great length, great arc, great circle, then that's what all these libraries are based on. So you don't have to do the calculation. You can take any 2 points on the Earth and say, what is the distance? Not as the crow flies. You don't go through the chord length. Instead, you walk on the Earth, a great circle. Already code has been written to find the distance between any 2 latitudes, longitude pairs. So I'll just draw the little part. Because you shouldn't think that just because the Earth looks flat to you, the calculations are all flat-based, okay? It's not. So what I'm saying is this. Suppose you're here at the equator, then, say this like Los Angeles. Then if you say, what is the distance from, some like Ecuador or something in, Los Angeles, then it's not this distance. You don't just simply find square root of x1 minus x2 squared plus 1 minus y2 squared. It's more like that. It's more like that. So between any 2 points on the Earth then. But how do you know what is the best distance? In other words, how is it not some crazy weird distance like that? You need to draw what is called a great circle. So between any 2 points on the globe, you can always make it go through a diameter, okay? So then that great circle, that arc is what you need to calculate. So all that is already factored into our calculations. So we don't have to do it manually. Also, while I'm here, one more thing is a longitude. A longitude is roughly like the x-axis, because it looks like the x-axis, right? So longitude comes first, comma, latitude. in lots of spatial data representation, because the reason is in the world we're used to looking at X and Y, because Y is like the latitude, right? North of the equator, south of the equator. Usually we like to say lat long, but lots of databases, lots of KML file format, all that would give you a long comma lat, and that is why, because long is roughly like the x-axis, lat is roughly like the y-axis. Okay. If you have never thought about all this before, it's like fascinating. Therefore, the main point is you have location, you have size. Autocorrelation just means just the way the world works. All of downtown buildings are in one location. All of farmland is usually outside, city limits. All of the business district is in one place. All of residential zoning is in one place. That is called autocorrelation. It just loosely means data of similar kind tend to cluster with each other. This is one amazing thing about spatial data that is not true about your GPA. You can zoom in and zoom out, right? That is what's so cool. So spatial data, you can zoom in and zoom out, like right here. Load it, like this. See that? That's very cool. By the way, these tiles, see, sometimes you can actually see, like, see, you saw that, right? The little gap that happened. Those are called tiles, and that is how data is stored. Sorry, it happened again. So they load data, not for the whole world, but right now exactly where we are. Then you can zoom in. This is the notion of spatial data having scale, okay? So you'll only see cities and street names and so on when you actually zoom in. Conversely, when you're going very far, you don't go street by street. You just literally scroll through the entire US like that. And so they're willing to give you data. Data is stored at multiple levels and even indexed at multiple levels, actually, okay? All right, so that is this idea. And then in addition to just having spatial data, you can also have time data. Again, if you look at the East Coast, there's lots of satellite pictures that tell you before and after like a massive, hurricane, what happened to like exactly the land there. It got eroded. And so in that sense, you have spatial data, but also there's a time component, meaning as a function of time, be the boundaries changing, the polygons are changing. Then it's called spatio-temporal, okay? So spatio-temporal data. So it is not standard data, it's something very special, which we like. It's very colorful, very beautiful, and it's about our world. Entity versus field. Mathematically, space is continuous. So we just simply call it field view. Like in calculus, you can draw a curve and then say, what is the line integral along that curve? So if I told you the analytical equation for the curve, then I can add it piece by piece by piece. But that is not what spatial data is all about. Spatial data it uses a different view of space called entity view, where we don't care that the world is continuous. We just care where, my school is and where my home is and, where my store is. So points, lines, and polygons. If you look at space like that as being made up of discrete entities, then we call it entity view. In other words, these are things that actually go in our database. This is simply for mathematical purposes. That's pretty much it. So we do entities, okay? Because roads, buildings, rivers, they're all entities. Prisons, airports, any of them. And then this is the part that I told you now, this makes so much sense to you. Your standard relational database, you already had it, okay? You still have like Boolean numbers and what, SQL. And then you index it using a B tree or, bitmap index, all that. But now this is the extra layer that somebody would add. This is where the points, lines, and polygon classes get defined. And then operators, which are things like area, length, volume, all of that. Classically, the word operator means like a plus sign. I can say, length A plus length B or something. And a function is just simply the name, the verbal name of the plus sign. In other words, plus sign is plus, ADD is add. They're both equivalent, okay? You can C++, the plus sign went away. I can always say add parentheses and then my variables, not the end of the world. So what I mean is there's not too much difference between them. So don't try and get confused about what is an operator, what is a function. They loosely mean they're doing computation on like a spatial data type. That's it. Okay, so then index is a very different way to index compared to a B tree. It's pretty fascinating, the whole indexing. So we're going to talk about all that. All right, so ultimately then a spatial database is built with types in mind, those types, points, lines, polygons, operators such as inside, outside. So imagine you have a CS building, already the Department of Public Safety knows the coordinates of the CS department. Suppose they have like our phones, GPS that they can track. Say there's a massive earthquake. They can very easily find out how many people are still trapped in the CS department because the database will literally tell them this particular point, this person's GPS is inside the CS department. So run in there and get them. That is very cool. That's also an operation, inside, outside. Or are two buildings touching? Without looking, can you tell me if this boundary and that boundary are touching? Or what about things overlapping? You should be able to just compute them. That is what all these operators are. And then indices, of course. All right, so spatial data is not just simply points and polygons, but even engineering installations. We work for Larsen and Toubro, Schlumberger, all these big companies, these massive, industrial construction giants. They build these huge oil rigs like out in the ocean. That might be like a quarter mile long. And so then all those coordinates for where the pipes are, where all the different things are, valves, they can go in a spatial database. So spatial database is used by the construction industry, like crazy. These days, people fly quadcopters and actually gather, GPS data and put them in a database. So there's like lots of things I can tell you. Agricultural data is also spatial data. How much rainfall happened, in the county? I can literally visualize them by numbers like that. And then three-dimensional data. So supposing this like a Hawaii, volcano or something, how are you going to store the spatial data? You can store them as layers. You can actually store like a flat version, and you can store the 3D separately, just the z values separately. That's called a digital elevation map. Okay, this DEM. Interesting. The same model. It's actually a digital elevation map. Okay, so DEM data. I'll just quickly tell you. In other words, you store XY separate, and then you can store Z separate. That is also possible. Then the idea would be you can use them separately. Like with the XY, you can learn how large the area is. With the Z, you can say how tall is my tallest peak. So this kind of data is called DEM. Okay, yeah. Okay, so you can see how, wow, the Great Continental Divide and then the Western U.S. Rocky Mountains. Look at how flat the Eastern U.S. is, except for the Appalachians. Very cool. Okay, so then you can store all of these at different levels. Okay, this is also something that, for example, Google Maps does, which is you can store all these as actual geometry data, like XY polygons. You can also store pixels. Loosely, this is called vector data. This is called raster or pixel data. Photoshop, Adobe Illustrator. Okay, they both have their uses. Okay, like in Google Maps, you can go in and turn the satellite view on. Sometimes you want to see what it looks like. Then that's a satellite view. It is only pixel data. There's no location, nothing. Okay. All right, so this leads to the cool question. So why do we even create spatial database? Like, what do you really do with them? Wow, you can put so many things on them. You can put crime data on them. Look at this. So I'm not just going to search for crime data, but watch this. I'll just say LAPD. Ooh, homicide, Honduras. Okay. LAPD online. I'll even just actually say LA Times. Okay, it's slightly different. Oh, the homicide map, that one. The homicide report. Scary stuff. See instantly, right? So plus minus zoom in. Oh my goodness. Okay, look at that. But now you can zoom in and zoom out, apparently, I think. Yeah, see that? It's crazy. And then for every single, this is all basically spatial data is what I'm saying. So murders are, very local, right? So if you want to buy like a house in LA, then one of the first things you want to do is, wow, tell me some areas I need to stay away from. And then a map like this becomes extremely important because, see, look, not all of LA looks like this at all. Sadly, the USC campus is like right there somewhere. Oh my God. Okay, but if you go out to Orange County, let me see if I can zoom out a little bit more. Yeah, I think that's it. So in here, yours truly lives, I think, like up here somewhere. So, just to make like an obvious striking comparison. So you can, if you can afford it, avoid crime areas. It's because crime is regional. This is all based on where the gangs are, unfortunately, what kind of things they're doing. So that's one of the biggest things that police actually does. They put crime data on a map. It's called predictive policing because then the algorithm tells them in what direction is the whole cluster of dots moving. And then they try and do what is called predictive policing. They send more police officers where they think the crime is going to happen because the data tells them, okay. Likewise, with COVID, there's absolutely any number of, oh my God, all these maps, right? But before COVID, there was a Zika virus, which actually was a pretty, bad little virus. It came from South America to a place like Miami. It basically makes babies' brains become very, very small and they become brain damaged for life. But you see at the border, the southern US border, Zika instances are quite large. But as you go out towards the north, they almost go to zero. But this was like a while ago. If you see an animation of this, then you see the red gradually spreading, okay? And so you can then see, wow, this is actually going all over the country. Sadly, COVID, it started in just local area and went all over the world, and there's any number of maps that do exactly the same thing. So maps are useful, especially for spatial data, disease plotting. Same thing with Ebola. So again, in West Africa, when Ebola breaks out, it's very local. Liberia, Sierra Leone, place like that. But then it spreads, person take it from person to person, and then the health department they go to all those countries and try and stop it. It's all about saying what can I do with this data. So this is Zika. I think there's an animation here, so maybe you guys can look at it another time. But yeah, it's like a whole, gradually it's now worldwide. People travel. Okay. Needless to, I'm just going to say, just say COVID map, okay, just to make an obvious point. There's like any number of them. Johns Hopkins, has like one of the very best ones. Okay, that's what I'm talking about. Just got a message. It's a big, big, big deal because it's how the world, the countries know like how bad they are in relation to other countries. Okay, wow, it's literally worldwide spatial data. It's one of the most striking examples in our lives of spatial data. What should I do? Okay, so COVID-19. And then this is something else that happened in the US, like a while ago, this throughout the 2000s really. OxyContin overdose deaths because there was a company called Purdue Pharma, and Purdue Pharma invented this most addictive painkiller pill called OxyContin, which is fine. Painkillers are good. They have a reason to exist. But Purdue Pharma paid doctors, bribed them all over the country and said, overprescribe this to your patients so that they get addicted, right? And then just insane what happened. All of the addiction started here in the Appalachia. I went to Ohio State, so I know all about this area. West Virginia, it's all like here, right? Kentucky. Coal miners, who work pretty hard, they're in a lot of pain. So they got addicted on the pills. But gradually the doctors, started prescribing this like all over the country. It became a scourge. It became this all like death map. So then every single one of the 50 US states sued them, and thankfully they're basically out of business, okay? It's like pretty bad stuff. There might be an animation somewhere. In fact, right there. So watch this, okay? So in 2002, look at it. Just completely local, right? Just exporting death, okay? They all knew, by the way, it's a bunch of basically a small family, brothers and sisters. They knew how bad it is. Their own doctors told them, but didn't care. They wanted billions of dollars. Just crazy. But the spatial map is so dramatic, like, wow. You don't believe what I say, just look at it. And then census data. So this again, I'm gonna show you what's called a dot map, okay? The US 2020 census just happened. And so I'm just gonna say census data dot map. And so, in a few months, they might release the results. What if every single person that took part in the census data becomes one dot in this map? One person, one dot. 300 million people, 300 million dots. Oh, come on, where's that? I just don't want all of this. Very quick. Oh, there it is. Okay. So look at that. Whoa. This is exactly what the racial makeup of the US looks like. Okay, 1.1%. Look at about 300 million people, right? This is 10 years ago. And so it's pretty telling, right? So the Caucasian population, is uniformly distributed like all over the country. Look at the black population, right? Remember slavery, was here. So then slaves, became emancipated. Slavery is over. They basically go north from wherever they are and concentrate in places like, Chicago, Cleveland, like so on, Detroit. And then the East Coast, obviously, and then also a little bit on the West Coast. Look at Hispanics, mostly from, southern part of the US. And then again, diffuse your way up to the north. In 2020, definitely this is not going to look like that at all. Highly more homogenized. There's a lot more mixing going on. So that is also fascinating how, how detailed this is. Again, one person, one dot. Wow. I don't own that site. Do you own that site? No. Okay, so that's cool, right? If you don't want racial stuff, oh, come on. Forget race, we're all the same race, human race. Then this is what the population looks like. The reason why nobody lives here is it's 1 mile high. Duh, these are the Rocky Mountains. In the West, usually the population is pretty low. But look at the East Coast, oh my God, and look at California. Okay, so then that is all what you can do. Income distribution, I'm not going to go through all of them, right? These are very useful. This is what Zillow, like Redfin, they all do, right? Basically take like public home prices and then they put them up on a map. And they do data analysis. And then if you want to sell your house, you plug your numbers in, and then it'll predict you what the fair value of your house should be. This is like useful stuff, very, very, very useful stuff. Because again, homes are like a pretty local thing. If you are Peet's Coffee or Coffee Bean and Tea Leaf, or somebody that wants to literally go up against Starbucks, the first thing you need to know is where's your enemy. So where are the Starbucks all over the country? I was going to say all over the world, or maybe all over the universe. Like, what the hell? Go to Mars and you probably find Starbucks. Look at that. They're everywhere. Once again, the reason why they're not in the Middle East, it's all mountainous. So seriously, you can buy these kinds of databases and then do analysis. So you do location analysis. That's what it's called, scouting location. Like, where can I optimally locate my store? Okay, so then that becomes like useful piece of data. Again, traffic is extremely useful piece of data, right? It's what Waze, Google traffic maps, they all do. It's super useful, like the live map. If spatial data did not exist, this whole thing called Waze wouldn't exist at all. And imagine how useful Waze is, right? You're driving and it's telling you, like, where the accidents are. So gosh darn cool. The Waze people, by the way, the Israeli programmers, in Israel, there's a highway that goes up and down. So they basically wrote it to help themselves. And they gave it to all their family and friends and said, we should all start using it. And it'll route traffic through like alternate, ways. And people just loved it. And then it became like worldwide. Waze is like a homegrown phenomenon because it is so gosh darn useful, right? And now Google owns it. Okay, so you should think of spatial data with all these cool things I'm telling you. I already showed you land use. What about deforestation, okay? So the Amazon rainforest in Brazil, it's pretty sad. You watch it, the deforestation map. It all used to be green, but now basically just burned, okay? Because, people want like land grow other kinds of crops and so on. Sorry, I'm just saying it's on deforestation map. You can animate this over time, then you really see how bad it is. Okay, yeah, so at one point, all of those are green, right? But then gradually, look at that. Like all these fires, by the way, people purposely set fires. And so that is also spatial data. Like the whole world should care because this is almost like lungs for the entire earth. So you damage your lungs, you're not going to be able to breathe, literally. So that's spatial data. That's spatial temporal data, okay, specifically. Okay, so who creates spatial data? This is pretty cool. Army people, because again, I told you warfare is spatial. Insurance risk manager. The Mississippi River, for example, can flood. If someone built their home right near the river banks, they have a high chance that the home is going to be flooded. So they'll file for insurance claim. The home is going to be destroyed. They'll come to an insurance company, pay me all the money. I paid you like a premium every month. So they should then pay a higher premium compared to somebody that's 20 miles away from the river bank because their house would probably not be flooded. So how do you then assess what the risk is? You literally plot that address on a map and then have a radius for the river and say, do they live within the flood zone or not? Literally how that's done. Even a doctor, like all your organs, your internal organs are all actually spatial, heart's in a certain location, so is the brain. And so the MRI data is also actually spatial data. Even DNA, the DNA molecule, right? It's a very specific sequence of atoms. You should think of as spatial data. It's very interesting, these things that we normally don't think of as spatial data. Yeah, I noticed that actually the first 1-year anniversary. Oh my God. Yeah. Astronomer, again, I told you, so these are like large spatial distances. So you can actually find out within like a region of space, a little slice of space. Tell me all the blue galaxies. Once you have all the Hubble data, you can do like analysis like this and find out how galaxies are distributed from the Earth's point of view. And then this is what I told you earlier. Governments take spatial data so seriously. The US has so many different ways of collecting spatial data, so many of them. So they have to coordinate, meaning you don't duplicate data, you don't like not share data. You want to, freely share, but also not do like extra work. And so then you have to, have this one agency called Spatial Data Infrastructure. Their goal is to coordinate, literally talk to all of them and say, what do you have? What do you have? Oh, you can use this, I'll give it to you. So make it all freely available, okay? That's NSDI's job. And then you can collect data. US collects data at the federal level, state level, and at the city level as well. At the federal level, for example, the Census Bureau that I just now named, National Oceanographic Atmospheric Administration. They track every single hurricane, every single tornado. I've been to that center there in Boulder, Colorado. Just beautiful, just absolutely beautiful place. They have supercomputers that actually do nothing but weather calculation and also tornado simulation and stuff like that. Just completely the weather people, okay? The only thing they don't do is earthquakes. And that is done by a different company, an agency right here in California. Who does earthquakes? Does anybody know? Like, what is the US agency that does everything about earthquakes? Yeah, exactly. Fantastic. US Geological Survey. I've been there as well. They're in Menlo Park, just north of Stanford, actually. I lived in Palo Alto. So it was so fun to actually go like look at all the mapping displays. You think that the globe, the map, the two-dimensional map looks a certain way. They have basically over 100 different types of map projections, okay? Because it's all just mathematical. How do you take a sphere and flatten it? You'd be surprised at how many ways there are. Wow. Anyway, see, these are fascinating agencies that is all spatial, right? Earthquakes are highly spatial, as you know. You live near the San Andreas Fault, you're screwed. Yeah, absolutely. This is so cool you put that up. I actually have in an upcoming lecture, data visualization, right? I totally show that. It's so beautiful, all those little arrows that move. It is highly spatial, exactly. Like little vectors, okay, that point out like what the flow of the air is. Pretty soon it's going to, yeah, that. Wow. That is what you can do with all your weather simulation, okay? You can analyze weather in real time or measure it even, just simply measure it and then just plot it. So cool. Yeah, okay. So when we have what are called Santa Anas, oh my God. Usually for, California, right? Winds flow from the ocean into land. But then during December, November sometimes, you get this horrible reversal of patterns when the wind actually blows from these hot mountains towards the ocean. But that is wildfire season. Sadly, all of LA catches fire. Then you can literally go in this site and watch the arrows go backwards. Like, oh my God, Santa Anas. Okay, thank you for that. Yeah, I was gonna put it up in the future. We'll still talk about it. All right. So then Department of Defense, these people, for example, say when the levee breaks, okay, the Katrina, the hurricane happened, then the Army Corps of Engineers goes there and actually fixes it because they know about spatial data. Defense Mapping Agency, they track where every single one of our missiles, every single one of our nuclear installations are. It's all about defense mapping. And then Bureau of Land Management, if you go to Utah, Arizona, Colorado, if you're a rancher, you want to start a farm, you need to go to BLM. This is the other BLM, by the way, as opposed to Black Lives Matter. So here what happens is this BLM has a database of every single piece of federal land that they have open for farmers and ranchers. Then you basically lease it, and then they give it to you for 10, 20 years. Not different from China, where you can own some land for like 17 years and build a home, but the government can take it from you afterwards, right? So it's not that different. And likewise, the U.S. Geological Survey, like right there. Department of Agriculture has like all kinds of. So I live in like La Crescenta, so a part of what is called the Angeles Forest. Sometimes you see trucks with like Forest Service logos driving around. So we have a U.S. Forest Service that keeps track of all the forests. Okay, that's like a lot. And then these are the ones that track like every single freeway. I talk about a 10 freeway, Highway Administration. So and then finally there's EPA. So these are all about pollutions, where all the power plants and where the nuclear plants are, all that. And then finally, if you look outwards, towards space, you have NASA. Although NASA does have so many satellites that look at the Earth, and then they can measure things like how salty is the ocean, how hot did things get. So NASA also collects lots and lots of geospatial data. So it's just amazing how much there is. Like, wow, if you have no idea, now you know. And then how do you actually create it? When push comes to shove, where do you get your latitudes, longitudes? On the one hand, like say the oil refinery thing that I showed you, I can go to AutoCAD, SolidWorks or something, and just simply draw all of it using my mouse. And then I can have actual distances, 100 feet, 200 feet, whatever. So that way I generate spatial data. Or I can go to an actual site and I can use LiDAR and then get a whole point cloud. So that way I can measure how far something is and turn all that into spatial data. For example, I'll just say like LiDAR, building measurement or something, building mapping. These days, you don't need a LiDAR. You can do it with the iPhone or a Google Pixel phone because they have LiDARs built into them. A self-driving car, does that as well. So you can take an existing city and turn all of those points into actual distances, okay? That's what LiDAR does. So I can instant spatial data. It's a form of reverse engineering. Reverse engineer, Statue of Liberty, for example, just make instant spatial data. Then I can analyze, don't forget. It's not just point clouds. Once I turn all that into a distance, I can say on the average, how long is one of these streets? Like magic, just get it. Yes, it is. It's a cool site. Okay. And then you can do it the old-fashioned way, okay? So cartography, surveying, and plotting. You see people on the street sometimes, what looks like a camera on a stand. They're measuring things like, elevation, orientation, and so on. And so then that is the old-fashioned way of mapping the world. I'll just say like one of these instruments. I'll just say surveying, plotting. We don't even have to say cartography. Surveying, plotting, that is exactly what I was going to say. So you can then move this around and basically map your whole area, okay? These days, the Google car has a camera on the top, and then it doesn't do exactly this, but it acquires the street view, but they can also do this because they're measuring GPS, okay? So GPS, by the way, is latitude, longitude, but also altitude. Your phone can even tell you, how high you are. Cool. So it's XYZ. And then if all else fails, you can send satellites up in the sky. Google Maps actually was not owned by Google at all. There was in San Jose a company called Keyhole Technologies. So Keyhole Technologies was bought by Google, and instantly that became Google Maps. So there are companies that do this for a living. And then these days you can fly like quadcopters and drones and actually collect GIS data. I'll just say quadcopter drone GIS collection. because you can put a little chip in there, right? You put your phone in there, and then it's going to come back with like amazing data and also an awesome video. And you can map the video and the data together, and then you have it. Okay, then it becomes that. You fly that, and you get that map. Too cool. Okay, so lots of different ways of getting data, spatial data. Tell you further, and then you can always walk around with the phone in your pocket, and then especially if you have like Fitbit, not particularly Fitbit, but similar devices that'll actually take you like for a walk around your neighborhood, and not just measure your calories and steps and what, but also it keeps track of the GPS coordinates, and then it'll plot on a map and say this is the route that you took. That's pretty funny. You can do that. So you can drive, you can walk. Okay, so now getting more deep into like exactly what you can store. You can store these kinds of data types that I mentioned already: points, lines, polygons. A point is just one data like x, y, longitude, latitude. A line is just a series of points, but then it's open-ended. You don't join it back like a road, an open road, like a USC campus gate from again west to east, like Vermont to Figueroa or something. And then this could be a building. So again, this looks a lot like a line, but the difference is the first vertex and the last vertex got closed. The closing then encloses an area. It doesn't have to be closed like a nice polygon like this. It can self-intersect. That is still considered, like this is also considered a polygon, okay? All you need is a starting point, ending point, to be the same. Then it adds up the areas. Likewise, a line can also intersect. It's still a line. All right. Polygons can have holes in them. Maybe this is a golf course, but the golf course has like a little lake in it. And then you could cut that area out. That's called a negative area. In other words, you have one set of coordinates, a second set of coordinates. Then when you say what is the area for the whole thing, it'll subtract this from that. So you get just the actual green grass. You can do that. That's all like here, okay? You can also store the same coordinates as not just x, y individual values, but more like arcs. We should ask you a question. Okay. How should I phrase this? Or let me just maybe tell you, that might be easier. So what is actually happening? I'll actually let them go. And again, this one. What is happening is something very cool with this whole arc stuff. Oops. Sorry. One more time, try it. There's a parabola. Okay, I'm going to show you the parabola to you. Look right here. So what is nice is this little part. When you have just 2 points, then obviously the most straightforward thing you can do is draw a line through them. When you have 3 points on the other hand, in other words, a line is just simply like a linear exponent of 1, right? Ax plus b. So it's raised to the power is 1, exponent is 1. When you have, on the other hand, one more extra point, I can now fit a parabola through all of them. I can fit like a parabola, right? Parabola. So now that parabola in general can be ax squared plus bx plus c. So y is going to be ax squared plus bx plus c, meaning I can fit between 3 points an actual like parabola. And you can keep going like that, okay? If you give me 4 points, if you give me any 4 points, I can fit what is called a cubic spline through them, a third-degree polynomial. So here, they probably use third-degree polynomial. That is why even though the database only stores those 3 points, when it joins it, it actually gives you a curvy line because it calculates the parabola coordinates, or it calculates the spline coordinates. In other words, it is not, so what is stored here is not this, more like that. Then if you ask what is the distance between all this, it'll give you that distance, not the distance, because that's actually what you want. Then it's called an arc when you do that. Arc, line, string, arc, polygon. A compound is both straight line and curve. It's called a compound. And then a compound line is again straight line, and curved line. And a circle is just a special case of an arc polygon. By the way, there's a theorem, right? How do you prove this very quickly? Between any 3 points, I can draw a circle. How? Just somebody tell me right now. No complicated proofs, okay? Like, just what can you tell me right now? Those 3 points, how am I sure that I can make? Yeah, right, that is true, but how do you find out, like, what's the center for the circle? I'll give you a big hint. If this was a compass, where do I put the compass point? 3 points, okay? 3 points. How do you draw the circle? Oops. I'll pretend those are the 3 points, okay? Anybody? Hint 1. Hint 1. Ha. Yeah, you're right. But then, no, you guys are not answering how to find the center, okay? How do you find actually the center? It's right here. Not angles. Getting pretty cold. Exactly. Perpendicular line from vertex to base. Very warm. Yeah, intersection of what? Getting super hot? Yeah, exactly. Intersections of what though? You still did not name the one thing. The one thing that brings it all together. What is it? The perpendicular bisector. You literally take the edge, divide it in half, draw the 90 degrees. Do the exact same thing. Divide it in half, 90 degrees. And if you do the third thing, hopefully it'll meet in the same place. That's the centroid, okay? Then that's going to be the center. And then you pick any vertex at all equal distance. So all of you answered, but it has to be the perpendicular bisector. Anyway, that is what's done here, okay? Let's move on. Fun with spatial data. All right. So then you can do more things like, define what is called a face. A face is another name for a polygon, by the way. So A can be a face. A can be this polygon that includes the boundary. B can also be another face. C can be another face. Edge is more like just a polyline or a line that's an edge. So 1 is an edge, 4 is also an edge. Remember, edges can be curved, okay, the polylines. And then nodes are just vertices. So vertices can be called nodes. This is just a different way of talking about lines, polygons, and points. Okay, then finally you can store rasters. Again, raster is just a bunch of pixels. You can store the RGB values. This way you can overlay this on like some topological data, and it makes, sometimes it's nicer to look at raster. It's more meaningful to us. Otherwise the line looks like that, so empty. Therefore, finally what I told you was in an actual database, you can store points, but you can call them by alternate names, or you can store lines, or you can store regions, or you can store pixels, which contains all these, but indirectly. So again, that's what happens. You take points, lines, polygons, and you form models. With the model meaning things like rivers and buildings, they're called models. And then the reason for doing all of that is you want to put non-spatial data, such as where's my customer, or where are my stores and stuff like that, or how far am I from the hospital? So where are the hospitals? So once you have spatial data, you can actually model like real world things with them, like lakes and highways and so on. And then you can add extra non-spatial features. The real purpose is that. Otherwise, you just have like a cool little database. And then you can do all these in different layers, like you can turn them individually on and off in a map. For instance, say the real world has like all these different things. The land usage, the city tells you this should always be a park forever. This should always be like downtown business district. This should always be residential where people build homes. That can be a separate layer. And you can find out how large they are, what is the distance between them. You can also store the elevation, just the Z value, as a separate data. Parcels, so what the city leases out to developers or sells to people, that's called a parcel. So parcel data from which this happens can be a separate layer. And then the actual map that you and I use, the street names and so on, can be a separate layer. And then non-spatial data customers. So take the address of all my Amazon Prime people and then put them on like a map and see where they're clustered. So that is non-spatial data, but on a spatial database. And then when you add all those layers, just conceptually, the idea is you're supposed to get the real world. But by breaking it up, I can do different analysis on different parts of it. For example, in the street level, I can say again, how long is an average street? Stuff like that, okay? Yeah, so keep it separate. And the same idea in a different image. This is really what you want, but then you can keep vegetation separate, you can keep buildings separate, you can keep streets separate. But then in reality, combine them. In many UIs, there's a checkbox literally for turning them on and off, and then you can visually turn them on and off. Okay, so this I already showed you one scale, okay? The homicide map, let's call it homicide map. Okay, so going back to the architecture, I flip back and forth between the architecture and also like what you can do with it to get the big picture. This is how it starts. You go this way, right to left. Take a standard database system like Oracle, and then you add this extra part. Even though you have like algorithms and all that, right? In reality, it's just this core part is data types and operations. I can circle it for you. Literally, this is all you want, because the rest are all in service of that, okay? So what we're trying to say is the main part is just that. No, sorry, not even that. The main part is that, and then that. All the other things just really are, in service of that. So once you add that, that's the API, the library. And then that data can then be stored in the DBMS as raw data, meaning only the people that write the libraries know to take a longitude, latitude, and turn them into good old like number columns and store them in the DBMS. But when you and I write software, like a map software, it comes to us as a point P dot lat, point P dot long, and then we do like standard point operations. We say, like p dot distance q, and then that operation would then go and fetch the data and then give me like a value, distance between 2 points. So in the end, we're just saying that the library is what makes it all possible. And that, in other words, any API has a lower level and a higher level. So we write our code at the higher level, but then at the lower level, the database does not even know this exists. That's what their API does. So the same thing in a different image. Okay, I'm gonna go a little fast. Again, good old DBMS, you can do all these usual things, but now we can do spatial stuff. You can do spatial joining, by the way. So spatial joining is when I can give you like basically the addresses of people and also like a map. Then you can join them and say what person belongs in what part of the city. You're joining data from like two different tables, but you can do it now for like spatial data. And then again, the same idea, spatial, this is really the core of it, data types and operations. And then the third useful thing might be the index, okay? Definitely this index. Then you can build like all kinds of cool things. You can do all these calculations. What can you do with all those operations? You can do like all of this. You can model data, you can do network analysis, visualization. And these are the real world applications people use. For example, Waze and Google Maps, that'd be like GIS, Geographical Information Systems is what GIS stands for. Geographical Information Systems, practically speaking, Waze software. All right, so therefore, GIS versus, so then I just now told you what GIS was. It is related to spatial data like on Earth, but the word spatial is more general. It can even be like molecular data, it can be galaxy data. Therefore, there's a difference between them. The difference between GIS and SD. This is more general, this is more specific. And even more importantly, this has to do with our Earth, okay? Yeah, then what do you do with GIS? You can do location analysis. For example, in a city, where are the so-called catch basins? So when it rains, what part of the city can actually hold the water, like a little, water tank? You can do terrain analysis, again, drainage network. So how is the water going to drain from the mountains, to the ocean? You can do analysis on that. It's all based on how the actual topology is distributed. And then you can do things like shortest path, like what is the shortest path from downtown to Venice Beach? You can take every possible way to drive and then come up with the shortest path. These are, by the way, classic graph algorithms. Okay, so in algorithms classes and data structure classes, there's a whole specific beautiful class of algorithms called graph algorithms. That is exactly what we're talking about. But now you can run those graph algorithms on spatial data, and it's extremely fascinating. You can do cluster analysis. You can do what is called centrality measures. There's one called betweenness centrality. Betweenness centrality. Yeah, you already know that, right? Yeah. Betweenness centrality. These are supremely useful measures that we've had in the world. Sorry, I said by the top. Oh, right there. And that. And measure the betweenness between like different clusters. Say there's a city, okay? The city is basically in two different, like people live there and people live here. That's basically a connecting point. But you can tell that without actually looking at the map of the city. The algorithm can tell you. So these are very fascinating measures you can do. But imagine being applied to spatial data, these measures. All right. So I should just let me back out of this by telling you there are things called centrality algorithms. And then you can now apply them to spatial data. There's many kinds, okay? Like degree centrality, eigenvalue centrality. These are fascinating. Not only that, it's fascinating, but also I can actually give you a homework. I'm not going to do it this time, but it is possible to actually give you spatial data and then have you code one of these algorithms yourself. It's actually possible. Probably not do that this time. Okay, that is all here, connectivity, spatial. And then again, things like proximity, what is close to what, again, you can do like analysis of buildings and so on. And then more statistics. Okay, I'm going to skip all this. Measurements. Okay, this is very easy. You can say again, what is the longest street? What is the largest building? What is the tallest building? Analysis. Yeah, these all turn into actual numbers, okay? So many of these turn into numbers. Other times, more operations I'm going to show you will not give you a number back. It's more like they'll give you a Boolean back, yes or no. For example, I give you a polygon and a point, and I ask you, is the point inside the polygon? There's no number there. You just have to tell me true or false. So many spatial operations are Boolean operations like that, yes or no. On the other hand, others are actual calculations, and then they'll give you like floating point results. So there's two kinds of operators. Okay, speaking of operators, these are all like Booleans, okay? Spatial relationships. Intersects, crosses within. Again, you can read up on them, but very briefly is all you need to know. Contains means I'll give you two polygons, and you're not allowed to draw them. You should tell me is one completely inside the other. That's a cool calculation to make. Like is one church, for example, entirely within one county, or is it overlapping some other county? Contains and covers are slightly different. Touch, are they exactly touching? There's no overlap. On the other hand, if one goes inside the other, that is called overlap. And there's different kinds of overlaps. And then disjoint is when there's like gap between them. So you can answer all these questions using SQL calls, okay? As long as you have the proper data in the proper format. And the SQL call will tell you true or false. It's so cool. Okay, different picture of the same thing. Disjoint, exactly meet, aka touch. Overlap, go too far. Covered by, contains, equal. Equal is interesting. Equal just means, suppose I take these same points A, B, C, D, E, okay? So I put them as one row of data, I call it A, B, C, D, E. But the next row of data, I call it E, A, B, C, D. I just scramble the I just permute the indices. I don't even mix them up, just cyclically permute them. So if I give you thousands of those, it's not easy for you to tell me, wow, these two are the same. But mathematically, it'll tell you, because it'll take every single permutation and compare it to what you give it and say equal or not equal. Okay, that's all. All right. This is slowly getting into indexing. So how do you index all this cool stuff? Okay, how do you get this stuff really, really fast? The answer is you don't actually index the polygons themselves or the actual windy road or the tall mountain, because it is too much data. It is too much calculation to find out how close it is to something, for example. Instead, you simplify your data. The simplification consists of what is called a minimum bounding rectangle. In 2D, it's a rectangle. In 3D, it can be a cube. And it is exactly what it says. It is minimum bounding. Bounding because the rectangle should touch your actual data. My actual data is this golf course, so I need a square that touches it. My actual data is my S curve, so my MBR should touch it. MBR for a bunch of points, like USC libraries, MBR. So it is bounding. It's minimum because I don't want a bigger rectangle. Okay, so for the same MBR, I'll just draw it for the heck of it. Okay, just humor you. It should not be wasteful, because we'll use the MBR as a proxy to find out if something is inside something or not. So if you have bad MBRs, you will get bad results. So the MBR for this curve, suppose this curve is what you want to actually find, is something close to this or not, okay? This should be the MBR that's a good MBR, as opposed to that's a very bad MBR. The reason is, if I give you a point, you meaning the algorithm, and I ask you, is the point inside or near the curve or not? If this was the MBR, as a first approximation, I would leave the curve alone. I'll find out if the point that is given to me is inside the MBR or not. And now the answer is yes. So I'll probably have to then do one more calculation needlessly to find out if this point is really near this curve or not. Thankfully, the answer is no. So I'll tell the customer no. But I had to do the rest of the calculation because the MBR lied to me. On the other hand, if this was the actual MBR, you see this point is outside. So even the MBR would reject it. Then I don't have to do the actual calculation. That is the value of a tight MBR. So what I'm saying is, suppose the point was here, and then I ask you, am I inside the golf course, yes or no? The MBR says yes. If the MBR says yes, I do the real calculation. The real calculation also says yes. Then it's yes. This might be what is called a, like a false positive, meaning the MBR tells me yes, but when I go and do the real calculation, the answer is no, and that's okay. I still get a no. But this would be a bad MBR that says even a point like this is going to mislead me and say, oh, you should probably find out. I find out and it's a waste. So no bad MBRs. Okay, these are bad MBRs. Should just touch. Also, the MBR, unfortunately, has to be parallel to X and Y. Why unfortunately? Why do you think I said unfortunately parallel to X and Y? All the MBRs I showed you, minimum bounding rectangles, you see they're all parallel to X and Y. Why is that a bad thing, you think? In other words, what can happen, what good things can happen when the MBRs don't have to be parallel to X and Y? Anybody? Look at the pictures that actually I'm showing you, then you'll have an answer. Let's actually focus on here. What about this? Lines at 45 degrees, right? Or some S curve or some windy road, what at 45 degrees are the worst case for these kinds of MBRs because they waste so much space. This kind of an MBR is called AABB. Wow, like in the game industry, graphics industry. Axis aligned bounding box. Axis aligned because you align yourself with the x-axis and the y-axis. Align means parallel. So this kind of a bounding box is called an axis aligned bounding box. So if you take game stuff, you do game programming, there's a different bounding box called an OBB. What do you think O stands for? It's not axis aligned anymore. It can be oriented. What if I make a bounding box like this? Just touches it. That's a beautiful bounding box. That way, all this false region won't be false anymore. This will truly tell you if something is near that river or not, right? That's beautiful. That is called oriented bounding box. Incredibly, in spatial databases, we do not use oriented bounding boxes at all. We only use axis aligned bounding boxes. One reason is the comparison is actually very simple. If I give you a point and I say is the point inside the rectangle or not, if statements here, if the point is, if this x value is more than this value, and also if the x value is less than that x value, and if the y value is more than this value, and if the y value is less than that y value. 4 if statements can tell me they all have to be true. If it is this, it's more complicated algorithm to tell me. If I give you like these 4 corners, okay, or 2 corners, if I ask you, is it inside or outside? It is not that easy, okay, because you cannot just simply do statements. Okay, so therefore, I guess for that reason, they don't use it. But it's very efficient, actually, if you ask me. In game programming, by the way, so if you punch a character, then the character would respond, depending on whether the game engine told your code, if the punch landed within the oriented bounding box or not. Game industry uses oriented bounding boxes. So therefore, if your arm was at some weird angle like that, right? Your arm was like this, what? Therefore, the oriented bounding box would be like this. You kick somebody, the kick landed here, then the person will not respond. On the other hand, if your kick landed here, then they'll actually check to see if you intersected the hand or not. If your kick lands here, definitely the character would kick you back. In other words, it tells the game what to do, okay? This is a very bad bounding box because then if you kick here, then you force the analysis to happen. You're just wasting like cycles. So we don't do axis aligned bounding boxes in like graphics and games. Okay, so in 3D, it's the same thing. This means if any point goes within this volume, then you have to do a real test, which takes a lot of time to see if that thing is actually in the teapot or not. On the other hand, a point outside is quickly rejected, okay? Okay. So then to finish this a little more, keep going. Yeah, so spatial relations. Again, the relation is just simply between 2 polygons, right? What kind of, calculation can you make? You can then classify all of those different calculations, all the different functionality into different types. On the one type, you can talk about what is called topology, which is you can talk only about interiors and exteriors. Like give me 2 polygons that I can tell you if one is inside the other or not. So these are inside-outside calculation. This calculation will actually give you like a distance. It'll tell you between any 2 roads, say 2 roads, I can tell you the closest point between them. So then that is like an actual analysis, right? So that is then called metric-based analysis. And this one. If I have 2 roads, okay. If I have any 2 roads like that, the road goes this way, and then some other road goes that way. If I ask you what is the closest distance between them, in this case, this might be the closest distance. So then the calculations will magically happen. You will get the distance. Or along the x-axis, just looking at this being the east, I give you 1 point, and I give you some other point. What is the angle between them? What is literally the angle between them, that angle? Then that is basically also that angle measure. So these are all pretty much, spatial calculations. So when you do functions, when you do measurements, then that is what I just now mentioned. Wait, skip something. Yeah, so metric-based is actual distances. You can also do direction-based. You can take a point and say, give me all the other points that are northeast to me. And then it does the northeast calculation. And then this is shortest path where I already mentioned this, okay, graph algorithms. So even though they're all functions, loosely speaking, but there's different kinds of functions. And then within topology, the whole interior exterior, you can talk about proximity. Is something close to something, or is something literally overlapping something, or is something completely contained in something? It's like a subsection of topological. So the long and short of all this is there are so many cool functions you can do, all just based on spatial data. And every spatial library in the world today supports all of them. So all you have to do is know how to call it, and then pass it some data, and then it can do like all this analysis for you. Without this, you have to manually do every single analysis yourself. So I'm going to ask you, what is that kind of geometry called? Where you're doing analysis on points, lines, and polygons. What is that kind of geometry called? For example, convex hull would be like a signature algorithm for the type of geometry. The convex hull finding algorithm. What was the convex hull again? The convex polygon that encloses all the actual points, right? So what type of geometry do you think goes into finding that convex hull? Convex hull, by the way, would have to pass through a subset of 8 data points, okay? Not 2D. I'm going to start giving you some hints, okay? It ends with the word geometry. In fact, I joke about it. I call it the other CG because it starts with a C. Something geometry. Ha. Now, not Hamilton path. That's a very special algorithm, not concrete. Exactly. Harsha is the right answer. It's actually called computational geometry, okay? So computational geometry is all about points, lines, and polygons. So go look at it. It's fascinating. So the reason to bring it up is it is computational geometry algorithms that are basically used in 100% of these. So someone has already done all the work. Plus spherical trig, like I said, that uses not just like a theta value in 2D, but also like a theta value and a phi value. Okay. In other words, you have an azimuth and an altitude, and also of course the R value. Okay, so then that's all already done for you. And then you can use graph algorithms. It's also done. So much of existing CS and math knowledge have gone into making all these libraries. So it's just a joy for us to use them. So then speaking of a joy to use, how do you actually do it? I'm going to show you a SQL. How do you find distances? How do you find areas? How do you find areas? How do you do it all? You do it all through what looks like SQL. But look, cool. This is simply a varchar, okay? You did this for your homework. The name of a county. In this case, what we're trying to say is, imagine you have California counties, okay? Then you give it one county, and then you say, what are all the counties that surround me? The California county map, okay? For example, Los Angeles County, Kern County. How do you, without looking, know what surrounds the county that I name? It's so beautiful. Imagine you have all the polynomial, the polygon data for all this, okay? So I can give you every single XY point for this, every single XY point for this. Then if I name some county, like say I name, Fresno County, it then is going to tell me, some Modesto and Inyo and like all of these, only the neighbors, it'll automatically pop out the name. Or I can draw a river, take a river, maybe the Merced River. Then I can ask SQL, tell me all the counties through which Merced River flows through. For example, it does not flow through Los Angeles County. We know that. But then how do you get the answer? That is all possible through SQL. Therefore, you start with a county table with the name of the county, such as Kern County. How many people live there? It's just simply like the name of it. The name of the state where the county is in, because every US state has counties. And then the population, that is just simply a number. But this is the cool part. The column name that is called shape is actually a polygon type. This is the new type that the spatial layer gives us. Because of this, this can be a series of X and Y values, which will close. And then it knows what the county actually looks like, okay? In other words, you measure like so many dot, 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 dot along like all of these, and then you turn that whole coordinate array into a polygon. Hey, cool. Likewise, also make a river, okay? So river is like an open line, okay? So once again, the name of the river and what city the river starts in is always nice to know. And how long is the river? And then this is the cool part, your actual geometry for the river. Again, I'll just say California, I'll just say Merced map. Merced River, even the county, same map. And you'll actually see. So that is what it looks like. And so then the Merced River starts here, goes through like a whole bunch of counties, okay? So we need to know the intersection of that county, of all the counties, and then that one river, okay? That's what's so cool, like that little thing. How do you do that? Let me show you SQL for that. Okay. California Merced River counties map. The reason why this is all like damn important is because in 10, 20 years, 30 years maximum, the world is going to have so much water shortage. We'll actually go to war with each other because, we're so thirsty, we're going to die. It's pretty horrible, right? Unless we do something. So then counties through which water flows. What if they start to dam, or what if they start to siphon off some of the water so that residents can drink it? Then the people who live at the bottom will actually run out of water because all the others already took it. This is happening already in Africa, okay? So the Nile, for example, flows from Egypt to like lots and lots of places. So the countries at the bottom, like, like Sudan and so on, they're not able to get water because Egypt and other countries keep all the water. They literally go to war with each other. So in the US, that is not that, hard to think that that can actually happen. So then you need to have what are called water sharing agreements. So the very first thing you need to know is, wow, what places, share this water? Like, in other words, who are all like seeing this water? Then they can pay and sell to each other. Okay, so now you see like the political reason to actually do it. So then imagine you have those two tables, okay? This is the new part you might not have seen before. So tell me the county's name. So first of all, take all the counties, make 2 copies of the table, alias them, call them C1 and C2. Give me C1's name, when any C1 touches C2. It means analyze all of them two at a time, but C2 is Contra Costa. Wow. So what this means is take the Contra Costa County and then go through all the other foreign counties that are not Contra Costa. Tell me if the touch Boolean equal to 1. You can literally do this, you guys, and you will actually get like a bunch of names. Wow. It's neat, right? And then likewise, the river, that example. So tell me all of the counties that intersect the river, but not any river, as long as the river is Merced. Wow. Then I can tell you all the counties and the river's name. This is going to say Merced over and over. You can take that out. Or if you don't say this and, then what will happen? Suppose I run this query and I don't have the and command. Then what's going to happen? What will the result be? I take out the fact that r.name equal to Merced. What will the query return? For a bunch of counties, for a bunch of rivers, all counties which have river, yeah, you're almost on the right track. Can you phrase it a little bit differently? You're right. All counties, and when you say which river, you can maybe phrase it a little bit differently. All counties, and the word all can be repeated. All counties and all rivers, which is actually what you're trying to say. In other words, for any river, if it touches any county, you will actually get the name of the river and the county. Wow. Okay, so that is cool, but it's useless, right? Because you want for this. So the and will then narrow it down. Hey, neat. You saw an actual SQL why this is useful. Okay, so just going back to the operators and function, telling you like way more about all this. Sometimes some operators, some functions as a return value, will return another piece of geometry. For example, if you give it two pieces of geometry and say fuse them together, like give me just the outline of both polygons, obviously the answer is a new polygon, right? So union command, union operator, would give you a new piece of geometry, meaning a new polygon. A difference is A minus B. Again, from this polygon, subtract the polygon. You'll only get the boundary, that little boundary. The intersection is opposite. What is common to two different polygons, okay? Okay, exclusive OR, like all that. A buffer is actually very interesting. In a buffer, I should actually draw a buffer. This is where the insurance analyst is going to come in, okay? So what they would do is take a river and automatically issue a buffer command. The buffer command would turn a length into an area. It will turn length into an actual polygon because it draws like overlapping circles. Wow. Okay, one more time. Right. Okay. So say you have a river, okay, like that. That's the river right there. Then what the buffer is going to do, the buffer command is, you give it like a line string like that, and then say, draw me a buffer, draw me a region, make me a region with the buffer of 0.2 miles. Then what that means is it'll draw like lots and lots of overlapping circles, okay, all with 0.2 miles like a diameter, we call that 0.2. And then take the tips of all of those and join them and make me a whole polygon like that. So it can turn a line into an actual area like that. That is what the buffer command does. Then you can say, does somebody live within the buffer zone, or if somebody lives outside the buffer zone? They pay a lower monthly premium. They pay a much higher monthly premium because the river is over here. This is all the river. So if the river floods, your home's going to be flooded. So that is called a buffer, okay? The buffer radius. That's what this whole buffer stuff is. Obviously, a buffer returns geometry. Cool. And then likewise, convex hull. So again, convex, I already told you, but just one more time, okay? If I give you like a bunch of points, no matter what the shape of the points is, the points can be like all like weird shape, but the result that I get back will always be a convex polygon. A convex hull can never be a concave polygon. It cannot ever be something like that. That is not allowed. It's called concavity. So that's a convex hull. That is not the convex hull. It takes it out, meaning it pretty much subtracts all the interior points automatically. Okay, so there's a pretty famous algorithm for finding the convex hull. You can look for it. Like I said, a signature computation geometry algorithms. I have implemented this in like C, C++, Java, Python, God knows what language. Okay, it's a fun thing to implement. Spatial operators. Whoa, I like 2 of them. Oh my God. Wait, everybody go away. Okay. So then spatial operators. So these ones, again, we've seen some of them right inside. So again, you can take some kind of a region and say, are you inside? Like literally like that. Inside, by the way, becomes so useful when you're driving. You say, I'm hungry. Where's the, Alexa, find me the nearest pizza restaurant. So your Waze already set some kind of radius from where you are, within like say 0.2 miles or something. Then within the radius, they'll search through the pizza place database and give you all the pizza places that are within your radius. And this calculation changes every second because you're driving. That's so cool, right? That is really what is so magical about this, is that you can turn all these, inside operations into when you're driving, I'm running out of gas pretty soon. So show me the nearest gas station, or somebody's having a heart attack, where's the nearest hospital? It's all about the nearest, okay, within like a certain radius. So that is like an inside operation. All right, so you can do touch, you can do coverage. I'll show you all this, whatever. And then just more of the same. Okay, I'm going to go a little fast because all these we've seen before. And this is the incoming, the foreign parameter. You're already a geometry. Then I give you some other geometry and say, are they inside you completely? You tell me true or false. So a function name, input, output, like signature. That's all this is. There's some other signatures will return like a distance, obviously. Because again, I'm a point. I'll give you another point. You tell me what the distance between the two of those is. Okay. I give you a line, like I'm a line. Wait, actually, I'm a buffer. I guess I'm a circle. I'm a circle of a certain radius, and then you give me a line. I'll then give you a buffer geometry. Literally overlap them. I showed you this. And likewise, given a bunch of points, I can give you the convex hull for it. Okay. So Meenakshi actually shared this with me, like you should pass student. Just a simple little PDF document that gives you like nice pictures of what all this is. Okay. So everything that I named disjoint, like all this, you can go read it afterwards. It's a systematic analysis of saying, what are all the possible operations between a region and a line, between a point and a line? They just go through it all. And so then the library, needless to say, supports all of them, like this, commands for all of them in any spatial library. We'll talk about spatial libraries very soon. Okay, so speaking of Oracle Spatial. So Oracle being the big granddaddy of all of them, they obviously early on had a spatial database library. In fact, they've gone through 2 or 3 iterations of the library. They even renamed them as they go along, the function calls. And the old function calls are still around. They're completely backwards compatible because they don't want to lose customers. But the latest offering is simply called Oracle Spatial. You can download that like a separate layer, they sell it to you. And obviously the reason is you want to do spatial type. User-defined data types, UDT. This means a class definition in C++ or Java. And obviously it comes with point, line, polygon UDTs, but also arc lines, arc strings, arc polygons. And then these are the methods. So once you have data, you want to have methods. All the things I mentioned previously are all methods. Okay, every one of these are methods. It's already done for you, just use it. How would you use it? You can do spatial analysis, you can do indexing. These are the things already part of the library. And then you build applications for them, okay? You can store points, lines, polygons. You can do all the calculations, if you want, the API gives it to you, the SQL commands, and then you index them. It indexes them for you. I haven't told you about indexing yet. And here's your core DBMS, here's the spatial layer. But in the end, people write these applications. The Grubhub driver is being led to your home, or the FedEx truck is being told what is the best way to bring the package to you, and on and on. Okay, so spatial data can be used for cool purposes. These are all APIs, by the way. So Oracle has APIs, using these web programming, simple. Basically, you're a client. The client sends a request in this, XML description, and then the server can then return data back. These days, you can replace it with something simpler, a REST API. So then you can send it some point, and then you pick some like a national park or something. Then there's a REST call. You send nps .gov, and then your query location, and then it can give you a JSON response back that tells you what the distance is. Curly brackets, distance : 2,000 miles. Then I'll know I'm 2,000 miles from some national park. So it's much easier than even this today. But the core idea is that they do the calculation. You don't have to do anything. Okay, so what can be stored? All the things I told you can be stored. Points can be stored, lines, polygons, and then ignore the topological part. Pixels can be stored. Geocoding just simply means there are databases that can take an address such as 940 Bloom Walk. This is CS department's address. And then give you the latitude, longitude that goes with that address. That is why in Waze you can type for Walmart, downtown Los Angeles, and then they turn that into an actual XY value because these libraries help them do that. Those libraries are called geocoding libraries. They turn human readable addresses into a latitude, longitude, point on the world, and then they can calculate distance and guide you there. All right, this is extra detail. You don't need to know too much, but what it is in Oracle and only in Oracle, regardless of what you actually store, whether it's points, lines, polygons, they're all called a geometry object. Meaning there's a wrapper object that wraps all the actual data types. And the wrapper is called SDO underscore geometry. SDO because spatial data operations. It comes from like so many years ago. SDO geometry. So everything is ultimately an SDO geometry. Inside SDO geometry, they have this thing called G type, the actual geometry type, which looks like this, which looks like that. In other words, say you take the number 3002 as an example. This means it's a 3D line string, meaning I drew a curve in space. I drew like some curve in space, and I gave it like all the x, y, z array of them. That is called 3002. On the other hand, if I have 2002, I still store a line string, but now it's all 2D, x, y, x, y, x, y, x, y, whatever. That is called line string. So 2 stands for 2 dimension, 3 dimensions, 4 dimensions. And then 1, 2, 3, 4, 5, 6, 7 stand for all these kinds of things you can store. Point is exactly 1 point. Line is 1 line. Polygon is 1 polygon. A collection is just, I think, a collection of any of those. I personally never use collection. Actually, I don't know what that is. A multi-point is many points, like a cluster of points, like all the students at USC. Multi-line string is many roads, like one set of them. And multi-polygon is all the buildings at USC. Okay, it's multi-versions of them. And then this is the part we can skip. This is literally the insert command. Okay, it's a little bit painful. You are actually making an SDO geometry, that's a constructor. But then you tell it what type it is. And then it knows to expect that. Because I told you 2002 means a 2-dimensional line string, okay? So imagine this is your line string. So this data, like right here, is encapsulated right there. But you have to go through all this extra crap to store just that. PostGIS, okay? Postgres is a very nice database. So for your homework, I'll have you use Postgres with a library called PostGIS. That makes it so easy to store just this little part. You can almost throw almost all of this away. It's as simple as it gets. So you should probably use PostGIS. And then these are the actual function operations. So given any one point, you would do SDO within distance, some other point. And then it'll tell you if the 2 points are within a certain distance or not, okay? Meaning, say you pick a distance of like 1 mile from where you are, then you can give it some other point and say, is it within like 1 mile or not? Okay, so then that's an example here, right there. Select city names and populations from like, cities, where the filter, this is location coming in. So I would actually give it some geometry. I would give it like some kind of geometry, and then tell me all the locations that are within the geometry, okay? Like right there. Then that's a filter operation. They call everything as a filter operation. And then finally set it equal to true. And so only those cities. You go to the geospatial coordinate, but then you'll get the city name. So all the cities that match like a certain query that you're trying to do. Relate. So again, the US is filled with counties, right? So I'll just show you all over. But what if you want the counties only within New Hampshire? Then you want to intersect the county map with the border of New Hampshire so that you can only get the New Hampshire counties or Iowa counties. County map, sorry. That. Very fascinating. A little jigsaw puzzle. Whoa. Okay. Crazy, right? This is the county map. So now, given all of this in like one table, you also are then given New Hampshire's outline. And you say, how do you then find out all the counties that are within New Hampshire? That is where the contains command comes in, okay? Cool. So then that's this like right there. So instead of contains, they're using inside and covered by. And then there it is. So all the states and then all the counties, but except the state name needs to be New Hampshire. And then you'll get it. Cool. And then touches. So this is just touching. So tell me if that county is actually touching, this. And then you can do the geometry touching operation. And this is the older version of doing it. I told you there are many versions of these API calls, so don't worry about it. And then is nearest neighbors. So this literally tells you from where I am within a radius of like 5 miles. Actually, sorry, it's not like that. Within a certain like a radius that you set, give me up to like 5 nearest neighbors, I think is what it is. So return me like some number of nearest neighbors, okay, and nearest neighbors within like a certain radius. 5 cities, for example, nearest to the interstate. We set that value and this that value. Cool. And then within distance, this is the one that I was telling you earlier. So this says within a distance of within a radius of 15 miles. Tell me something I'm looking for. You get that? Like this is your location, your car, and then give me all the buildings that are within 15 miles, a certain type of building. Or in this case, it's a highway, but it can be a building. That's all it is. So just do distance calculations, spatial calculations. I'm a tiny bit behind, but it's okay. Let's do spatial indexing, okay? So indexing is like again one of the most useful things you will learn from like all of this, which is how are we able to do all these calculations so fast? Again, the answer is you have to pre-sort the data somehow, which you call an index. And then when the actual calculation happens, you don't look at your whole US map somehow. Somehow, if you're able to pre-sort it, imagine for New Hampshire, searching only these counties. That'll be a lot faster than searching like through all of them, right? Because it's useless to say, oh, you're inside New Hampshire. There has to be some spatial way to do it. And so I'm going to show you a bunch of them actually. They're called region trees. A region tree is more like an overlapping series of, like a hierarchy of rectangles. Meaning I make one rectangle and I say this is a root for all the counties. At that level, all counties are equal. Then I'll make another smaller rectangle, another smaller rectangle. They can even overlap. And then say at my next level, my left rectangle, only these counties. My right rectangle, only these counties. And then I can cut those into even more smaller rectangles. So I'll form a hierarchy, like a tree of rectangles. In fact, those rectangles are actually minimum bounding rectangles, MBRs. That tree, the hierarchy of rectangles, is called an R tree. R stands for region, a region tree. Then if I want to find something, it's almost like a binary search. I would go in the region tree and ask the very top box, the point that I want. Am I inside the big box? I probably am. Then I'll ask the left box and the right box. Am I inside you? Am I inside you? The right box says yes, the point is inside my big right box. The left box says no, you're not inside me. Then guess what? You don't have to go down that path at all. Literally just cut the whole number of counties by half, like a log search. Then you take this box, and this probably has 2 more, 3 more boxes. Ask them, where is my point? 2 of them say, no, you're not inside me. This rectangle says, yes, the point is inside. So now you cut down 2/3 of that half. Then you go down this point. So within just a few operations, you can get to where you want. Magical. Okay, so that's all coming here, okay? All right, so spatial indexing is used for query performance as usual. It's a region tree based on MBRs. I told you all this, okay? And then you can index in any number of dimensions, not just 1D or 2D. Cool. Okay, so you can index everything within that. You can put points on polygons and very quickly get to them. Then the reason is for doing that is this, like I told you, a real polygon, a real county map has pretty irregular boundaries. Then if I want to know if my point is inside some county or not, I don't have to do the expensive calculation right off the bat. I can use this MBRs, which is pretty easy to, say in and out, to do a 2-level calculation. So every SQL query that is spatial would actually run in 2 levels. In the first level, only R trees are used to eliminate things you don't want to look at. So things that pass the R tree test, there's a smaller series of data, actual data points. Then you have to do your real test on just a much, much smaller bunch of data points. Then you will get your exact result. If you don't do this, you're spending so much time on your entire raw data, okay? So the rectangles help you throw like so much data away because it's easy to do rectangle calculation. So now you understand. All right, so Postgres, PostGIS that I just mentioned to you, it's like all of here, common functions. Just some FYI about this, okay? Sorry. Okay, so then these things I've mentioned before. In fact, the same thing was in a slide previously. These are the actual operations you want to make, and these are the incoming parameters, and then these are the return values. Many are Boolean, some are actual data. So you know all this, okay? Overlaps contains length. And then I did this like, just for fun to show you guys this a couple of years ago. You can just make a table just like that. Create table, insert into county. So this one is PostGIS, okay? So easy, just insert values. And then these are the column names. This is the column parameters, rather, meaning this is the name of the county, And the geometry shape, you have to say this, okay? The line string just means the actual data. Geom from text means take that string, the text value, and convert that to an actual geometry internal data type. And then not any geometry, turn that into a polygon. So like 3 constructors, okay? It's happening here. And then you get your polygon, and then ignore that part. Then you say, show me the polygon. It shows you in some crazy encoded format. But now you can start doing other kinds of analysis with it. You can say, what is the area of what I just now gave you? Or what is the length of this line string? You can actually ask in SQL. All right, so if you want to do all this for your homework, you can wait on this, but this is what you would do. You can install Postgres. And then there's a nice shell called an application stack builder. You can do it all. Okay, so I'll give you much more instructions in the future. Right now, don't worry about it. The one thing, at least remember this right now, okay, for now, which is just because you install the library, you download it, it doesn't mean your SQL query would work. It'll actually tell you shape data type unknown. I don't know what you mean by shape. You have to explicitly enable every plugin. They're like plugins. You need to tell Postgres, please load the spatial data plugin. That is called create extension. So you need to do that, okay? Enable, you need to enable that extension basically. Then it works. Okay, so you can wait for the homework instructions. And SOAPOST.js.net has everything. So this can tell you much more than I told you. See all these examples. Again, remember, this is all the raw data, but you need all these extra, things to go make them into actual objects. Then they can operate on the objects. See, they have so many other things, right? But in the end, again, points, lines, polygons, so don't forget the basics, like distance calculation. If you, have time, if you're patient, if you actually copy and paste all this into your shell, you will learn so much about how this all works. Okay. But the point is, we never have to do any of these calculations ourselves. They just do it for you. We can use so many kinds of map projections, okay? Again, I told you, the world is inherently 3D, but then the maps are all 2D. So you need to have some kind of a distortion somewhere. And so there's many, many kinds of them. So based on what those distortions are, any 2D calculation that you make might actually give you different results for things like areas and lines and angles and so on. So map projection types. Therefore, you can specify, to your engine what kind of projection is your data in. That is what that was about. There's so many projection types, like so many of them. They're all used, by the way, cool trig math, okay, if you're fascinated. I have a whole PDF full of them, so if you actually mail me, I'll send it to you. Yeah, I study them just for fun because they're cool. Okay. So you can then specify what, actual coordinate system you're using. That is what all this is, things like, transverse Mercator, like all that. Okay. So then in the end, it just goes on and on like that. See, then these are the actual polygons and then like lines. And you can do calculations on them. This page very nicely explains like everything that I told you. Which means if you have any doubt, then go here and you'll fully understand. Okay. So we should keep going. Yeah, so spatial indexes, so how do you create indexes? It's like this. You do the whole R-tree stuff. First of all, a little side tour. I'll go fast because it's like not useful at all. The point is ultimately that you have spatial data that is not just like a column of numbers. Say you have 16 numbers, 1, 2, 3, 4. You want to somehow know very quickly that if my mouse cursor was here, somehow 2 is near me, 1 is near me, 16 is not near me. I want to index all the spatial data. This is a very simple square of spatial data somehow. The question is how, okay? One way to do it is, this is not how it's done in the real world, is to do what is called a space filling curve, okay? So space filling curve is literally, what if I take here I should draw, what if I take a one-dimensional curve and somehow make it be two-dimensional? That is called a fractal, what I just told you, like this. So what if I literally took a so-called fractal curve that went like this? Do a little fractal curve, like that, little fractal curve. I don't want that. You go pick up the pen again. Draw. Okay. Okay, that. What if I do a fractal like that? So this says 1 and then 4 and 13 and 16 are like a boundaries in a way, meaning at a first level, I'm indexing this whole space into 3 different pieces, okay? Things that are near the first segment, things that are near the second segment, things that are near the third segment. Then this first segment, I break one more time up into that. And then I go like that. And this middle segment, I break one more time up. Then I break this segment one more time. I break that segment one more time. So from one Z, I went into smaller Zs. So now that is where the recursion is, smaller Zs. Then that small Z, I can go into even smaller Zs. So that is called a Z curve. Okay, so Z curve. Z curve is a Z recursion. So I drew that over there, but I'm going to show it to you here. Watch this, okay? Oops, I'll try it again. Make this button go away. Okay, so look, what I told you was exactly that, which is if I draw initially just my first Z, then it's as if the Z can be straightened out. A Z is a two-dimensional curve. But if I pull the Z, so it becomes one long line. Along the line, I have then region 1, region 2, region 3. So region 1, region 2, region 3. Within those 3 regions, I can map all the actual spatial points into saying these all go in region 1. The middle part, like all this and all this, go in the middle region, and all this go in the bottom region. Then I can draw one more region within the region, make a smaller Z, and then subdivide. So just watch this, okay, like that. So that's the first level, second level. So I draw Z's within Z's, and then I join them all together. That was a fractal right there. This means any point in my actual city is all laid out along this one-dimensional straight line that starts here, ends here. That's what this is. Then if you give me some point and I ask you, what is the building near me? I first start at the largest level, and I ask what segment of the Z should I look at? And then it's only going to be 1 or 2 or 3. I pick the first, it's going down in 3. Then for that first segment, I say there's still three more at the lower level. Which one should I pick? So I'm going from that biggest Z to a smaller Z to an even smaller Z and quickly finding what I want. So it's a one-dimensional curve that is actually useful in 2 dimensions. It's a very weird idea, okay? It's a very weird idea that nobody in the world does it except Apple. But even Apple, they don't use it for your, maybe iPhone or your Apple Watch or something. But Apple does have one database called Foundation DB. Shockingly, as far as I know, this is the only database where they, for spatial indexing, they actually use a Z curve. That's what all this, okay? It's just crazy, okay? So they're using a Z curve for indexing any spatial data. Wow, weird. Okay. FYI. Okay, so this is what I just explained to you. Other than that, it is purely of academic interest, meaning, wow, look how cool this is, but nobody does it because there's better things to do. This is the better, easiest thing to do. Imagine that your actual buildings you want to very quickly locate on a map are A, B, C, D, E, F, okay, all these buildings. So you start by saying, I'm going to make at a top level. The top level, by the way, for these trees don't have to be exactly just one node. Even the top level can have multiple, whatever nodes. Okay, so I have A here, right? That is the big rectangle, A rectangle. Then I draw a B rectangle. Then I draw a C rectangle. The C is hard to look, but it's like right there, little C. That is what this is. Then within A, this means D, E, F are all within A. D is over here, E is over here, F is over here. J is also within A, right? But I want to put J in C because J is in both C and A. You only want to include one time. So then J went to C, okay, so it's not an A. B is pretty simple. B has G, H, and I. Imagine, like these are the real buildings, these D, E, F, G, H, I. And the A, B, C are all just simply rectangles, meaning these are the leaf nodes. These are the actual gas stations and hospitals and so forth. But you start from A, B, and C. And then C then has all the rest. The idea would be that you are standing here, and they say among all the buildings, among all these leaf buildings, so which one is the closest to me? So then I take my point right there, I plug it in A, and I say, is my point here within A? The answer is no, so I don't have to look at these at all. Wow, cool, right? I'm here. I'm definitely not within B at all, so don't even bother what this is. But now I'm in C. Wow, now I have to look at it. And so who are all within C? KLM, JKLM. Then I have to do a distance calculation with JKLM, only 4 calculations. And then I'll probably find that L is closest to me. I would output that. So from all those calculations, I'm now down to just 4 calculations in this simple example. That is how you can dramatically speed up things. You're avoiding going down trees, exactly like a B-tree index, okay? But now it's all done based on spatial calculations. One more example, say ABC, you can go through it yourself, same idea. The idea is just pick something and then start with the largest rectangle and say, where am I? I'm inside A, so I'm not inside, B and C, for example, like right there. Then I can only examine D, E, F. But imagine doing this to 2 or 3 levels. Then maybe you can not even have to do any calculation. You can quickly just get to F, okay? Okay, so then it's a hierarchy. It's a hierarchy right there, of bounds. These are all just bounds. Because your actual building for F might be like entirely different. This was many years ago. So people then said, wow, how can we make this even better? So there's a whole bunch of research that is done on these variations of R trees with names such as R star trees and buddy trees and so on. So you can like Google them, there's like research papers on them. You can maybe come up with something even better than all this, and maybe the whole world would be the, pat to your door. Yeah, I'll definitely get to KD3 totally. It's smart. Yeah, there's so many other variations, okay, which I'm going to tell you. In the game industry and graphics industry, we use what are called quad trees and K trees and KD trees. So I'll tell you about those. Or even BSP, binary space partition. So this is definitely not the only way, but R trees are pretty simple. And then they can also overlap. These R trees don't have to be spatially apart. You can have overlapping trees. It's a pretty easy thing to code, okay? But speaking of variations, so NJ said KD3 is right here. A different way to organize the same A, B, C, D, E would be to start with one of them, hopefully in the middle of your whole data, if you can tell, as your root node. So A is literally how you'll partition the whole world based on the fact that A is down the middle. So imagine then drawing a line down A, okay? So your whole world is now divided into 2 parts, left and the right part for now, starting with A. A different way of saying DBC would be on the left-hand side and A is going to be on the right side, like a binary search tree. But now what would you do with that though? So now how would you index like BCD? I would pick something in the middle of this whole data. B is unfortunately the only middle, but the line that I draw through B is horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, alternate. That's why B is now a new tree, but with the line going this way. That means something is to the top of B, something is to the bottom of B. Sure enough, that's C and D. They are the leaf nodes, and you can just stop. Actually, for that matter, U and AB are all nodes. Actually, here there's no difference between like roots and like leaves. Anything can be anything, but you would use actual buildings, actual features in your data set to draw a tree. Then it's called a KD tree. On the right hand side, again, you have to index E and F somehow. Draw a line through E, draw a line through E. There's only one thing on the side of F, this on side of E, nothing on the other side. This is empty, but that's okay. Okay, and then you put your cursor right here, and you say, what am I closest to? Looks like a bad example. I'm not going to do it now. I'll do it here, okay? So what am I closest to? That point that I'm clicking on is definitely to the right of A. So I take A's own coordinate, my coordinate. So wow, I'm going this way, okay? Then compared to my coordinate with E, I'm now on the right side of E. What is on my right side? F. Oh, quickly got to F. So one hop, second hop. So easy. A KDB tree is still the same data points, okay? The exact same data points as before. But now you don't draw the boundaries. You don't make the tree through actual data points. You do it around the space that surrounds all your data point, meaning take the square and pretty much bisect the square. It doesn't matter if the bisection does not pass through any data point. You don't care really. It's optional. Then you get that. Meaning first level, second level, third level, and sadly here there's no fourth level. They all become like leaves, okay? Again, the idea would be that I would take my actual data point and very quickly go down this line. So no need to look at all this. And then for this one, I'll very quickly know that I'm on the up part of it, not the down part of it. So I only have to do 3 distances to find out what is my closest point is. All just ways to save time, okay? You see it. Then it's called a KDB tree. Okay, so quad tree, arc tree, they're very similar, but this again based on recursion. Now what you do is here I can actually draw it. Depending on where your actual data points are distributed, you would do cool things like further subdivide or not further subdivide. That is your only choice. So initially, imagine that these are all like, okay, so imagine these are all like cities or buildings or something you want to index, okay, very quickly. So I take the boundary of my whole city and I draw I draw 4 regions. It's called a quad tree because I take my region, quad tree, right there, and divide them into 4 parts. Then I look at each of the 4 parts and I say, wow, can I bail? In other words, can I stop subdividing? Is my recursion bottoming out? I would know to stop when my region is completely empty, okay? Or in my region, there's only 1 point, there's no point further subdividing, only then I stop. Otherwise, I'll not stop. Right now, for my little red lines, I'll go to a different color. I'll not stop because there's something here, something here, something here. I'm going to draw one more time. Second level of recursion. Second level. Then I'll look into all of these 16 regions and say, should I subdivide, yes or no? All of the 16 regions have something, so keep going, okay? That is how this works. So subdivide. But after a while, see what happens. There's nothing here, right? So no need to subdivide that anymore because it's a complete waste. You'll still get nothing. So stop that tree right there. On the other hand, this right there, subdivide. After that, no need. Subdivide, no need. Because these are empty, these are exactly 1 cell in them. So build a very cool tree that is highly asymmetrical, okay? And that tree always will have, if up to a maximum of 4 branches because you're doing quad. But at some point, the branch will stop having children because you don't need to subdivide anymore, no need to subdivide. It can be an imbalanced, like a bunch of, like always split by 4 array trees. 4. That is called a quad tree. And then the idea is the same overall. Then my point is here. Then I'll go through my initial tree and say, which of the 4 directions should I pick? Just pick that direction. So then no need to look at any of those, all gone. Wow. So within that point, should I pick this, or this? Just pick that. No need to look for all this anymore. So within this, which should I pick? First one, no need to look for all this anymore. Wow, sorry, you're standing in empty space. But it's good that I know that, okay? I still no need to, I don't have to look through all the extra points. That is the idea. So quickly, one way or the other, you'll know like where you are. It's a quad tree. Okay, cool. Therefore, each is either a leaf node or exactly has 1 point. It doesn't have to be 1, by the way. You can decide to stop when a bucket, these they're called buckets. Buckets have maybe like 2 or 3 points, and you can just stop. That way your tree won't be like very deep, okay? But it's like hash collision. So if your bucket that you stop has 5 points, then now I have to do 5 calculations. On the other hand, if the bucket that I stop has exactly 1 point, I'll basically reach my answer. So no more actual manual, no measuring anything. So you pick like what to do. In 3D, it's called an octree, okay? So octree is how, for instance, Minecraft might be run. The whole Minecraft world is an octree world. It's like quad tree, but done in 3D, okay? They're called voxels. So in 2D, they're pixels. In 3D, they're called voxels. Okay, so like all of that. This means I can take my spatial data. For example, I have a tree, then I can make an octree version of my tree. And the character is running, and I would know I'm under the tree or not very easily, okay? By subdividing space into 3D versions of this tree, okay? Yeah. So it's called octree subdivision. You can take your brain data from your CAT scan and then actually do it in 3D, and that is how the surgeon is able to slice through your brain. I'll just say octree subdivision CAT scan data, then you'll actually say it. Meaning we can take the measurements that we get from a CAT scan device and build an octree depending on where the bone, the neurons, like all the different layers are, fat tissue, your brain connective tissue, axons, glions, all that, glials. And then you make this, then the idea would be the same. You only subdivide when there's some data to subdivide. All these regions, no need to subdivide. Then you can very quickly then slice through them, meaning go in any orientation, and then just go through all those voxels and easily reconstruct data. Okay, so spatial subdivision of data. Almost done. And look here though, right? Binary trees. Again, these are all evolution, okay? Like how did we get to our trees, okay? So this is very cool to see that KD trees are here, KDB trees are here, and then there's R trees. So R trees conceptually came from B trees because it's the whole idea of subdivision, the binary subdivision in a way. And then they got the idea of region tree. But see, R trees evolve into R plus tree, R star, like I told you. This is still 1990s. So imagine, after all these years, after 30 years, we have a lot more, but probably, still cool stuff is sitting out there to be discovered. Cool. Then the reason to, do all of this in the first place is because, like I told you, if somebody says, give me all the rivers that flow through Merced, give me all the counties that Merced River flows through, you should not take the actual county polygon shape and start intersecting that with the line shape. It's too much. Instead, you should deal with rectangles and throw most counties away, and then only deal with a smaller subset of counties that can possibly the river can intersect. So that is called two-level processing. The first level is called filtering. Throw away the bounding boxes that don't match, and keep only the bounding boxes that match, including possibly false positives. False positive means the bounding box says yes, but the actual calculation says no, which is fine. So in our case, first of all, let me read. It tells you, so query region just simply means with the mouse I draw like a little rectangle. Then I tell you, give me all the buildings that I just now drew a rectangle through. Then your real answer should be C and B, right? A is clearly out. The bounding box for A is not even overlapping bounding box for my query. So then we don't have to consider A. But look at D. D is an interesting case. D's bounding box makes it seem like it needs to be inside my query region. So I will actually end up examining C and B and D, but I would throw out D because in reality, this point is not intersecting my actual triangle. But that's okay. Yeah? In reality, I can throw away millions of these and probably have like 20 false positives. But the real answer that I should get is B and C because the actual polygons intersect my region. But see my two-level query, right? In my first level, I throw away that. My second level, I throw away that. That's my real answer. So two-level processing. It's pretty simple, but so useful. Okay, we can finish with some visualizing, just some fun data visualizations. One way to visualize points is just simply literally plot like little points right there. This one is unfortunately, sex abuse, okay, like Washington, D.C., 2009. Abuses by victim age, so children, adults. So sadly, disturbingly, there's so many children like all over the place. But a dot, each dot, one incident. Those are like dot map, examples, okay? And then there's something called, let me show you what I have here. Here, racial dot map, I already went through this. So this is the same of what I showed you, but one dot is one person, like 300 million of them. You can also do on a map, on a spatial map, what is called a proportional symbol map. So now this is like a bubble chart in the sense, you don't even have to read the number. Just the radius of the circle tells you something big is happening. In this case, mean family income in like thousands of, US dollars. So the people that live here make on the average $50,000 a year, pretty rich people overall. Compared to here, they make $8,000 a year. That is a crazy amount of difference, right? Like 6 times difference. And they're like, wow, what is happening? Maybe you need more data to find out like why is there such a big difference. That data might come from somewhere else. In the meanwhile, a different kind of a map that's not proportional symbol is called a diagram map, where I can draw little bar charts, okay? So again, the taller the bar, the more the income. Again, obviously the taller bar and obviously a pretty low bar. Literally right there. These are the same thing ultimately. Or you can do a pie. So now you get a better sense of like what is happening. We take those same numbers, you take the same numbers, but now you start to say, show me the ratio. So sorry, this is about actual numbers for income. Okay, so income, income, income. This one is only about races. Forget the income. Tell me what type of population distribution do we have? This one says predominantly 3/4 literally whites, Caucasian population. Here, almost 100% black population. Wow, maybe race has something to do with income disparity. Okay, in the real world, sadly, that is true, right? This is how social policy gets made. So somebody then the city would say, wow, how do we fix it? Well, we need to have businesses open there. We need to encourage people to go and shop there. So then maybe, hopefully, after like a decade or something, this will literally come up, right? That is the hope. But then you need to know like the brutal but sad answer. Wow, maybe it's racially divided. In other words, this is exactly correlated with that. Like what other reason are you going to have? This is more noisy than that, possibly, but noisiness does not cost like so much levels of income, right? So the whole idea is somehow it is race, somehow it is tied to education, it is tied to opportunity, but all that comes afterwards. The raw data just bluntly tells you, wow, this is why. So that is exactly what you can do. Little pie chart at every single spatial location. And then there's something called a choropleth. A choropleth map, these are not choropleths, none of them are. Choropleth means I can put my finger and my mouse anywhere on the map, I'll have a value for it. Like a fully filled map. In this case, it is called a classed choropleth. These are called classes. Classes means ranges. So anything that is a higher range, I'm going to call it that color. Anything that's a very low range, I'm going to call it a different color. Class choropleth. If this classing goes away, I have a more continuous color. And it's a continuous choropleth, okay? So a class choropleth versus a continuous choropleth. This is also classed in a way, I would say, because it is going for a US state. A USA Today weather map is continuous because you can see it. You can see this every day. It's probably like a weather map. If you stay in a hotel or something, right, you pick up your, open the door, pick it up, and there it is. And so those are pretty much continuous. Like see that. So there's no range at all, okay? They can obviously make a range if they want. This seems like more like a range, right? But then a lot of times there's no range. There's no separate key that tells you what color is and what. Then that is called a non-classed. This one is classed on the other hand. Okay, just only two kinds. Easy, move on. Well, we should then finish with libraries. Okay, so everybody that sells or gives away relational databases, they have a spatial extension. They have a spatial library. What is in all these spatial libraries? Exactly what I told you. Spatial data types, spatial operations, spatial indexing. Three things over and over and over again. It is because underneath it all, SQL lets anybody write custom classes. So they all did it. Hired people that know computation, geometry, or graph algorithms, and said, write some functions for us. And then it's done forever. Okay, so then functional extension, spatial, all this. Oracle, again, they have many names. Now they call it locator. In the past, it used to be called spatial. It used to be called STO before that. Postgres, always the layer is called PostGIS. This is the only one where you don't have to actually install PostGIS separately, okay? So if you install Postgres, it includes the PostGIS installation as well. Wow, IBM mainframe going back to 1960s. They have an old BB2 mainframe. People still buy. Their extension is called Spatial Data Blade. Sounds pretty scary. Blade means layers, by the way, in computing. We use the word blade to mean a layer. So that means a spatial layer. Informix, which is actually not part of Oracle. In the 1980s, okay, 3 companies in Redwood City, right in the middle of the Silicon Valley in the Bay Area. Informix, Sybase, and Oracle. Wow. All of them competed head to head. All within like 2 or 3 miles of each other. And today, only Oracle survives. Wow. All right. Fascinating. But information, I used to have a geodetic database. And then Microsoft SQL Server, they have a mouthful. GGG, I guess G cubed. Geometric and geodetic, geography types. What the hell? Stop it. Let's call it geometric, okay? Okay, so then MySQL also, just install MySQL, you're gonna get it. And then SQLite's simple little DLL file is called Spatialite. For your homework, by the way, when I give it to you, You're welcome to use any of them. You just use them. You can find the IBM mainframe to it. But I think the easiest way to do it is to do that. You can do this for fun, by the way. If you do it with this, you can use Python or etc. to actually very easily use extra map libraries and then actually plot your data on a map. Whereas here you have to do a little extra work. But just pick one. All right. So speaking of your homework, I'm going to give you spatial data, like locations to analyze, or how you pick it up from a map. That data comes in a very specific format called a KML format. KML is so cool, okay? It is basically like an XML format. And then you can use it to describe. I'll tell you much more during the homework. But then right now, I'll just show you like one example. Yeah, it's just pure XML. But then it has words like latitude, longitude, polygon. And you put in numbers in there. And the neat thing about storing data in this particular format looks like that, okay? Just blow it up a little bit. Literally, like that. You would say that's XML encoding, and then like right there, and then place mark. Every point is called a place mark, okay? And the actual points coordinates, longitude, latitude. You see, it's like above the equator, probably like near LA somewhere. And then this is like notes, name. This is what will show up on your map actually. You can literally drag and drop this into Google Earth, okay? It's like 748. Hey, why not? You try it. Okay, I'm gonna copy it, just to show you that's possible, okay? Because you can do this with your homework as well. And then you can start to change all this data yourself, meaning you can type in like new data from your Google Maps. And then it's gonna be so cool. Okay, so I literally just got this. I'm just gonna call it fun. We'll find out where this is in the world, okay? Say fun. Okay. By the way, this label cannot be too large, also be aware of that. Okay, so I'm gonna call it fun.kml. Then here's what you do. You can actually start Google Earth. The nice thing about a public file format like that is there are so many programs that are written to make use of that format. Okay, so OpenLayers is different. Let me actually do Google Earth. You can even do it out the web, by the way, earth.google.com. But let me see if I have it, okay? Yeah, Google Earth program. Okay. And launch. Okay. And then you just drag and drop. Spin, spin, spin. Whee! Okay. Okay. Can you drag and drop? Hopefully. Ooh. Go, go, Earth, go. Whee! Wow, look. A little parachute jump. There it is, right? And so that is what's so cool about it. You can just turn it on and off. So it's an amazing format, okay? That push pin, if you don't like it, you can even define your own. You can define like a little bunch of polygons and it'll draw that. You can group them. You can have a hierarchy of them. You can have a thing called UST libraries and literally put every single library and make the like layer for it, okay? Okay, this is a neat format is what I'm going to tell you. You'll have much, much more time to explore it. Okay, so that's what the whole KML business was. This is called Keyhole Markup Language. I told you earlier, Keyhole was a satellite company that actually flew satellites and collected lots of data from the sky. Google just bought them for a few $1 billion, and then Google instantly got KML. And also, more importantly, they got Google Maps and Google Earth instead. Just add water. OpenLayers is an alternative to Google Earth. If you actually use Google Maps for your business, say your Uber or something, you need to pay a licensing fee to actually get the maps. Okay, the maps are not free. On the other hand, if you don't want to pay anybody any money, you can use something called OpenLayers that also has spatial data, and they give you an API. And then here's like JavaScript version of that. Okay, there's many other APIs as well in Python, etc. You simply just start doing stuff. I don't know what I should do. Custom, I don't know. Custom polygon styles. Just pick one. Okay. So they're all just a few lines of JavaScript. Okay, and then the map is all loaded automatically. Is the Polish? I know. Okay. No, it's not Polish. It's Canada. All right. So see, that's JavaScript, right? Good old simple little JavaScript. And then you can then literally give it some like a point, and then it's going to generate for you. And then you can put it in HTML like that. And then there it is. You can easily deploy applications, full live applications. You can actually do stuff. See like that. I don't know what I'm doing here. Okay. In some of them, you can actually draw like 2 points, and it'll tell you what the distance between them is. So please go look at OpenLayers. It's a fun little API. I might have you use some of this for your homework actually. Okay. The homework is going to be very simple and fun in the sense I will get some points, and then do all sorts of plotting and or analysis on them. Okay, ESRI is the biggest, most powerful geospatial software vendor of all. And they're right here in Southern California, Redlands. ESRI, Environmental Sciences Research Institute. Cool people. Our USC grads have been hired by them, right? If you like spatial databases, and they make it like so much cool. Okay, it's like you spend like hours and hours on this. Okay, it's all about the maps. In fact, even the Johns Hopkins COVID map actually was based on their what's called ARC software, ArcView, ArcGIS. Okay, ArcGIS. People just make all this and just put it up. Okay, what you can do is, by the way, they have APIs to make maps. One way to make maps is drag and drop. They have a drag and drop interface where you can drag and drop points that you like say all the art installations in Los Angeles, and then you can share your map just like that. So you don't even have to be a map software writer. A second level that they have is a little bit more programming, a tiny bit more programming. Just simply connect some components together, and then you can deploy the map like on the server. The third thing you can do is actually write Android, on iPhone kind of applications and actually make like map software. So they have 2 or 3 layers in which people can actually make maps. Okay, it's all in here somewhere. Developers and like products and solutions. So cool. But the flagship product is basically ArcGIS. Okay. Yeah. Okay. Just so much, too much actually. Yeah. Because they make location like basically a no-brainer. They're just telling the whole world, give us your data as long as it is spatial. We'll take care of the rest for you. That's a very powerful thing. These are things that people dream of doing in the past, right? But they just couldn't. But then this just comes and says, just give us your data. Do it for you. All right, cool. And then it can be used for really neat things like this, okay? Like environmental sciences. All right, so CAML, ESRI, spatial database. One last slide. Then maybe it's break time. Quantum GIS. See here, this software should probably cost like tens of thousands of dollars, okay? But it's entirely free. So you can download QGIS and like I have it installed. You can then drag and drop the same KML and it will actually show up there as well. And they have many algorithms, all built in and it's completely free. They use, I think, Python Qt library, and you can do all the neat things in there. So install that if you want and play with it. Okay, just show this to you. See, again, like all of this, it comes with all the map types and just plug it in. Okay, like that. Again, remember the visualization is like one nice element, like how do you actually see it? It's all responsive, so it looks nice on your phone screen and whatever. But more importantly, all of this part, analyzed data, okay? That's really the core of it. I mean, there are so many algorithms, I told you. It's many people's PhD thesis, okay, they're all in here. And then they have plugins through which people can extend this even more. So you can really do anything you want with it. So it's radically powerful, but always free. Okay, so then that. And then other APIs. So some of these things are not free, by the way. So Mapbox is all entirely cloud-driven. All these are cloud-based, by the way. So these days, what happens is you take like tons of spatial data that you have, and then upload that to a cloud. In this case, Mapbox, and start doing analysis. Okay. So that is the whole trend of all this. Is that you don't have to have your own server that has PostGIS installed and do stuff with it. Let somebody else do like all that. The thing that they don't have that you have is data. Okay. And then the thing that they have that you don't have is all the analysis and all the plotting. So then they both meet. You pay somebody for it. That's it. Yeah. Cool. Okay, so that is Mapbox. And then Carto is very similar. After a while, they're all like competing with each other. Carto has a JavaScript version called Carto.js. So just in 2 or 3 lines of JavaScript, you can do neat things with it. Okay. Again, see, like why? That's the key question always, like what is happening? How can I explain this? Okay. Everybody in the world can use it. Even cities can use it. LA, by the way, I'll tell you another time, but LA has actually LA City. In fact, it's called geocities.lacity.org, something like that, where they have nothing but geospatial data. Our mayor, is actually data friendly, and so he has a separate hub, Geo Hub, I think is what it's called. Okay, so all like spatial data. Okay. In this case, traffic data. That's exactly what a city would want, right? In other words, Caltrans would say, wow, I want to visualize like a real-time traffic, map. They have the sensors that they put on freeways. But then how about the software that actually visualizes it? Then rather than writing it on their own, they'll probably go to Carto, just buy it. Okay, the last one is GIS Cloud. Just like the name, that's what it is. It's a GIS cloud. Cool. Okay. This is neat, right? It's instantly on a map. So you can be anywhere like in the world, right? And basically tap a button and then your coordinates are sent to the cloud and then the whole world, just automatically up the map just updates. Wow. Imagine you're a field worker. Imagine you're again in Africa looking at Ebola patients, right? So your phone, anytime you go to a patient's house, just open your phone and tap an icon and say send data. That's it. Then the whole world would know there's an Ebola patient. So if every single field worker does it, you'll know wow, this is where the epicenter for the whole outbreak is. We need to go there and stop those people from going somewhere else. So that is a whole real-time analysis. I tap some button and magically you'll get a little orange dot there. Waze works like that, right? Because if you enable Waze, then anybody can see like where you are because you're this little smiley icon that's driving around. It's the same idea. You can update these in real time. Real time is magical, but you'll come to that much. Look at that. These are like big numbers, right? It's the JS Cloud can do it. That was a very interesting, I hope. A little bit fast-paced, but there's not much to say. A tour through the world, the magically fascinating world of spatial data, which again comes down to this very abstract, simple, high school, points, lines, and polygons. But when you pair that with what the world can do with it, then it's like truly magical. Because almost everything we do in our lives, believe it or not, it has a spatial or a temporal dimension, okay? Almost everything, believe it or not. Therefore, these things would become more and more useful in the future. All right. So I'm, like about 10 slides is all I wanted to do for, NoSQL, but forget that. We'll do it next time. So let's take a little break, maybe like a 7-minute break. In my clock, it is 7:58. So let's come back at 8:05. So we'll have 15 minutes to do some mini review, okay? My review, by the way, is very simple. It looks like this. That's all my review is. So you can talk for a little bit. I'll ask you some questions, okay? So we should be back at 8:05. Bye. All right. We're back. Let me share the screen. Share. Hey, check that out. OMG, it changed. There's a new guy. Can you guys hear me? Oh, cool. Okay, thank you. All right. Hey, your name's almost like rhyme. Garima Karishma. Cool. Okay. So, thank you, Cheng. It's just a doodle, by the way. So it's basically just like a doodle, and then it just simply went from there. These things have no actual purpose. There's no like a direction. Just play with ink and pen. All right. So what happens is, how do we? Time for you guys to ask me some things about the exam. First of all, the exam is not fully created yet. So I have some questions ready, but then not all of them. So it is like a Schrodinger's cat. Oh, thank you. Yeah, no, that's funny, right? I actually went to like Open Ocean, I think is what one of the sites was called. Yeah, right. 60. Can you believe that? Yeah. Oh my God. Yes. Unbelievable. Because it is not fungible, not fungible. It is fungible if I take a screenshot. Oh my God. That makes it fungible right there. Okay. That is the part that the crazy people don't get. That's fungible. Okay, I made a copy of it. All right, so back to our point. Oops, please become non-fungible. Yeah, exactly. Yeah, that is, as long as it is tight, the coin that it comes with, right? But as an art form, like we just said, it has no value whatsoever because it is good old pixels, right? Yeah. Value is what those people make it out to be, which I think is pretty silly, honestly. But hey, I'm not paying for it. I'd love to be paid for it, but cool. So let's go here, okay? There's a bunch of things we talked about, obviously, right? There's like a lot of concepts, starting from ER diagrams. We'll revisit this in just a minute. But the reason why I put this up is actually, it's important. Yeah, exactly. The value is decided by people, which is true for all of Bitcoin, by the way. Bitcoin should basically be worth nothing, just a bunch of numbers. But look, $100,000. Wow. Okay, so the key question becomes, what do you do? I think the one word, you probably got that from the sample midterm, was actually to understand everything, understand. And, many times you're not used to actually even like really realizing what that means. It's a simple word, right? I understand. But understanding is not just simply knowing like point by point what is in every slide, because that is what a lot of people are used to, studying for an exam. That is how they study. I just know everything that somebody said. In machine learning, that would actually be called overfitting, and so overfitting is not a good thing at all. Okay, it means you actually didn't learn anything, believe it or not. It means like what to repeat, that somebody said. So please, please, please do not do that. In machine learning, undersampling is absolutely to look at nothing. Okay, just simply make up like whatever the heck answer you want for every question. That is also a very bad idea. So please don't do it. The truth is somewhere in between. Okay, you want optimal fit. So for us, what that means is just really read between the lines if you need to, and just really know what I told you. If I bring up the answers, I can actually show you. It is like such a simple thing to write. Oh, I cannot believe that the answer is only 2 lines long. So it is not that it's only 2 lines long, but the answer is like a interesting, important answer. You don't need to say more than that. That's the point. Reviewed by going through Piazza. Yeah, that is actually true. In Piazza, some cool questions do come up, but I might not use those. So although good explanations, like Ritesh, for example, posts like some pretty neat things. And so do other students. Basically, he's our lead TA, as you know. Yeah, right. Yeah. Those are nice, but I actually don't pay attention to all those at all. It's good. It's good for your own benefit in a way. But this is literally what I mean, okay? You don't need to write more than, 2 lines, 2.5 lines. So you can keep your answers really, really short. And there's always like so many of the why and what. If you notice, okay, there's a word why there, right? And then there might be a word why somewhere else. See, when is it not acceptable, right? And this one also is like, when is it acceptable? When is, by the way, why? Like, whoa, like what is the circumstance? It really should be, why is it acceptable? Under what circumstance? So please always think about the why, okay, more than the what. The what is the easy part. What is what somebody would ask you, what is a transaction? Well, a transaction is usually made up with more than one read and write. But Alexa can tell you that. But a more interesting question might be, why do we care? So what is the big deal about trying to manage transactions? I want you to probe that. Like literally ask yourself, wow, why is this a thing? Like, why does two-phase locking work? Why does two-phase commit work? That is called thinking. And so that is all this is all about. This was not covered, by the way, last year. I didn't tell the students about data flow, but you should read this and be able to know what is happening. This looks like SQL. In fact, this looks like a SQL tree. It looks like a SQL closure tree, because no matter what operations you do in SQL, you get tables, right? So which means you can sequence them. This piece of software is a real piece of software. It lets you drag and drop from a menu all these operations, okay? Like there's a table read operator, a join operator. So anything you want to do through SQL commands, you can visually do it. And then see how powerful this is. Just imagine an analyst who does not want to learn SQL. They're a business person. They can then do joins themselves, okay? Because if you click on it, a property would appear and you can pick column names so you can tell it like what to join. 100% visual, and then they can get their answer out on the right hand side. So I'm asking a question about that. Like, why is this a big deal? Because anybody that is not a programmer, because the whole world is mostly not a programmer, they can also do self-service, data analysis. Then you say, what is the flip side? Like, why would you not want to use it? Because someday you actually want to do something pretty powerful that at least as of now, the interface is not offering. Maybe in the future they might, but as of now, they're not. So at that point, programming is still handy. So, go learn your SQL. So I want you to give me answers like that confidently, okay? But I should stop talking though. So tell me what we should talk about. Go back. You can even ask me what type of questions would be there and stuff, I mean, I'm not going to give it away, obviously, but I can answer you if you're concerned about, like how to study or something. I almost told you. There's a philosophy, meaning there's a way of thinking about the world. It's called cross-cutting. So if anything, if there's any pattern in basically all my questions, it is about cross-cutting, okay? So cross-cutting literally means this. It just means there's some concept over here, maybe parallel programming. So I'll definitely explain closure. That's a good question. Maybe there's another concept here. It's about data. So then, data and parallel processing absolutely come together. That's what the whole world of big data is all about. So what we should do is not think of things as individual islands. Not that this is a ER diagram, and then this one is more about, data types, and this one is spatial data, what. You should always just say what connects them. How do you weave threads between them, okay? That is what's called cross-cutting. So in my own life, I think about stuff like that a lot because in the real world, hardly anything is like an island unto itself. Everything is ultimately connected together. So please think of those kinds of, in other words, this might be in lecture number 1, this might be in lecture number 12. I might ask you a question that actually needs for you to go back and forth like that. So unless you already thought about it, it might not be obvious. So it's not a hard question because if you look at the answer, it's like 2 or 3 lines or 2 words or something. So it cannot possibly be hard, but it basically, like throws a curve, right? And it throws a curveball. In other words, it basically forces you to do something new. Is what it is. Therefore, practice that. Just practice. Ask what is the connection between many different things that I tell you. How should we review? Yeah, for that, I think the answer would be know the concept and possibly pick a table that is not normalized at all and go through the whole exercise of finding out where the partial dependencies are, where the transitive dependencies are, and draw the diagram that has the arrows on the top and the bottom. That might be a highly useful way to do it. I'll definitely tell you closure. What to study from connectivity. Right, so connectivity, yeah, the word theory, so I would not use that word at all. I mean, it's a common word. I'm not faulting you. A theory is like so different. Okay, a relational. I mean, I can tell you, a relational algebra theory, to make it actually a theory, is completely mathematical. Okay, so we're not doing that at all. We're keeping it very, very, very practical. So theory is the opposite of practice. I'm not going to say this is theoretical at all. What it is you might say the word abstract if you want. Although that's not even the right answer. You're probably saying it is not concrete enough. Okay. Yeah. So the theory would use those operators and then use math. I'm not even seeing some good examples. Anyways, it looks nothing like what I taught in class, okay? So let's not say that, but instead we'll say, how would you approach that? Again, I would think about it from a practical point of view. Like why does, for example, a web application server exist? What is its purpose in life? Or why did they enable CGI bin, so what can that do? So like all about why, what. That's what I would do. Yeah, exactly. So you don't need to know more than 3NF, for this course at all, because in the real world, it's actually not useful. So to answer Cheng and Yash, that's what I would do. I would just say, what is the purpose and what does it help us do? Like, what can we not do without it? Just be practical about it. Nobody asked me about SQL. There was a SQL question, right? But you also saw that the question did not ask you to write SQL from scratch, because that is pretty cruel, right? You got like time, the clock is running, not going to have you write a SQL query at all. Most of you would not be able to do it. It's cruel because if I give you like more time, right, all of you would be able to do it. So I won't ask you to write a SQL query at all, but there might be a question basically like this, like what does it do, or how can you make this a little bit better, or what is wrong with this? Like, I wrote this, but it's not giving me what I want. So how can I fix it? It means you already have a starting point. That is the answer to your SQL questions. So there might be a SQL question. More likely, there's going to be, for sure, it's going to be one. But it is not something that you have to think of SQL from scratch. Or it is also not something that you need an actual live SQL interface to type something in. It can be answered, just by looking at it really and doing some analysis. Yeah, exactly. So the why questions can be open-ended. So many of the why questions actually are open-ended. Some of these, by the way, are not, okay? These have real implications, like consistency versus, availability. So then I'm not going to say open-ended in the sense you cannot write anything you want. But in stuff like this, it is a little bit open-ended, like that one. So why do you need to hand code queries? Again, we don't use exact words that we look for, and there's a rubric that says, unless they wrote flexibility, give them a -1. It's not like that. In that sense, you're open-ended because you can write almost different things that say the same thing. But you cannot say something entirely radically different. For example, you cannot say hand-coded queries are easily compiled by the SQL compiler or something, right? That is not true at all. So it's not open in that sense, okay? It still has to be reasonable. It still has to be right. I know everything you put about the Linus Fair game. Yeah. There isn't, the honest answer is, I think if you get what I told you literally, if you understand, this is probably one of the easiest preparations in the world. You go like, wow, I almost need to know nothing because I followed like what he said. There's nothing that I told you is so horribly hard, okay? That's what I'm trying to tell you. Like say the Viterbi algorithm as an example. Not that it is hard, but it's a very specific algorithm. So you don't know how the algorithm works. And there's a question using the Viterbi algorithm, you would get a 0. So it is not like that in this class. Almost everything we've gone through, they've all been like straightforward. There's a reason for that, by the way. The reason is we don't have a formal prerequisite for this class. We used to have 485 as a prereq, but then we took it away. It means we have 350 something students. And so they come from all kinds of backgrounds. See, if you make this like more complicated, more mathematical, then we'll actually lose like a lot of people. And so therefore we just keep it, fairly straightforward. Is the BI content? No, not today. Not the one today, but from last time, yes. There's actually a thing that is here. All the content above this line are included. I guess is included in the syllabus. Okay, but yeah, nothing from today. It means some of BI for sure, yes. What else? 8/19/56. I'm gonna get a warning that says sorry, out of time. So I hope everybody does well. Okay. In the meanwhile, if you have actual questions, please post on Piazza. We'll answer as many as we can. So the exam is Friday evening, as you know. Don't forget you've done the practice. So it should be hopefully very straightforward. Almost no computation, almost none. Yeah, closure. Closure is very easy. I'm going to go really fast, okay? Talk to the den operator. If you give me 2 or 3 minutes, I'm going to do closure. Closure, okay. It's an idea where data types of some type give you the same data types back. Okay, so here's a table, right? Here's also a table. If I join them using some join condition, the result will also be a table that is called closure. Say I have a third table. If I then take these 2 tables and if I do an intersection operator and then I find out what rows are common between these tables as long as the operation is legal, then that's also a table. The idea that you can keep going from the same data type to the same data type, which means I can infinitely chain them. That idea is called closure. What is called breaking closure is something happens and you cannot do this anymore. Suppose one of those was a min operation, okay? Suppose min operation. The min operation will give me a number. At that point, closure breaks because you cannot pass another table to min, right? So that's not closure. So closure is the same data type being given to you over and over. For example, in simple numbers, addition gives you closure because the result is also a number. And then sort of subtraction gives you closure. But then negative square root does not. So square root, by the way, does not give you closure. In this case, you get closure. But what if the number instead was that? All of a sudden, this cannot be expressed in standard numbers. I need a bigger type. I need a complex number type. Therefore, square root is not a closure operator. In that sense, join all those was closure, but square root is more like min. It breaks closure. That's all closure is. It's neither good nor bad, but it's good to be aware of what it is so that you can do the right operations, not break it. It just is. Closure just is, whether you want it or not. So then in the databases, you'll know what will break closure. All those column operations, such as min, max, count, average, etc. Okay. All right, everybody. I think the den people want me to stop. All right, so good luck. See you Friday. Bye. You're welcome. Srirag, Christian, Ramani, Malaki, Yash, Krishma. Cool. Good night. Stop. Atashri. You're welcome.